Good morning, everyone. Ladies and gentlemen, welcome to the SAIEE online seminar entitled Distribution Network Planning for Renewables. The seminar is powered by the Load Research Chapter within SAIEE. My name is Monde Soni. I'm the chairman of the Load Research Chapter, and I'm not alone. I'm with the executive committee that will be chairing the next proceedings. The next sessions, it's Lloyd and Marcus. You'll get to know about them just in a few. Some webinar considerations. Seminar considerations. We would like you to please submit all your questions in the chat box, which is usually on the right-hand side, top right on your webinar, GoToWebinar screen. And also please do note that you are muted. So the only way to communicate with the presenters is by using the chat box. And we are really looking forward to those questions. The second point is that the questions will be answered during the Q&A session, which will be at the end of each presentation. If it happens that we are not able to answer to attend to all the questions at the end of the presentations, the questions will be sent to the presenters in a form of text, and they will attend to those questions and they will be published. The answers to those questions will be published together with the presentations. If it happens that during the presentation you lose connection, for whatever reason, please don't despair. The presentations will be published on the SAIEE website under the Load Research page. And also these presentations will be recorded and be aired on SAIEE TV, which is a YouTube channel. So we have catered for that eventuality that if we lose connection. Our program is packed and I'm sure that you are all going to enjoy it. And we are also looking forward to it. Now, our presenters, our speakers are what I call heavyweights in the subject. I'm not bragging, but you will also see for yourself. Please do engage with them again, using that chat box. Now, on the health front, just a few notes about COVID-19, which is the pandemic that everyone is dealing with currently. COVID-19 is real and it is with us. It is deadly, it's killing people. So we really need to be careful and ensure that we stick to the basics. And also as engineering practitioners, we must just remind ourselves of the Engineering Act that in everything that we do, we need to be aware and at all times try to save lives or preserve lives and the environment. And that includes situations like this one where we've got COVID-19. As the Load Research Chapter, we made a decision at the beginning of the pandemic that all our engagements would be done online. That includes panel discussions, seminars like this, meetings, etc. Let's all do our bit to help to curb the spread of the virus in all our corners, whatever we can do to make sure that we escape the spread of this deadly virus. On a more lighter note, happy level 2, everyone. Let us please keep winning. And I think within level 2, we are free to go and get some goodies. Please do enjoy them responsibly and ensure that you're still keeping to to the regulations, to the safety regulations. With those words, I would like to officially open the seminar, and I say, let's sit back, let us relax and enjoy. If it happens that you feel hungry, we have arranged tea, coffee, biscuits, all those nice things. You can find them in your kitchen cabinet. You can also grab some cold drinks as well while you're at it. That's all available in the kitchen space where you are. We have arranged that for you. Ladies and gentlemen, without wasting any more time, our first presenter of the morning is Dr. Mbuli. Dr. Mbuli is a corporate specialist in grid planning at Eskom. He is also a senior research associate with the University of Johannesburg. Dr. Nhlanhla has got ME and a doctorate in engineering. He will be presenting to us a keynote address for this event today. His presentation is titled Evolution of the Renewable Energy Landscape in South Africa and Options for Network Planning. Dr. Nhlanhla, you will get the screen now to start sharing your presentation. Thank you.
Okay, thank you. I wish to thank first the members of the organizing committee for inviting me to make this keynote address. Is everything visible from your side, the program director?
Yes, sir.
Okay, let me just close some of the things that are on my way here. Yes, as I've indicated, I wish to thank the members of the organizing committee for this seminar for inviting me to make this keynote address. I also wish to greet the members of the Institute and other guests who are tuned into the seminar in various places. I've elected to talk on the subject of evolution of renewables landscape in South Africa for power generation, and also to make some considerations on options for network planning. Okay, sorry. Yes, the layout of my talk is as shown there. I will commence by touching briefly on how renewable energy for power generation has evolved in South Africa. And then with the consideration of the changing levels of renewable energy, I will talk about approaches to planning, hosting capacity of networks, and then I will move to talk briefly about capacity upgrade of lines as one potential option that can ensure economic integration of renewables, and then I will draw a conclusion at the end. Electricity is a key requirement for the operation of the economy and for creating habitable environments for human beings. As a result, as economies grow and more people are connected into the grid, we will see a massive increase in the installed generation capacity globally. In fact, it is estimated that by 2050, we will have reached about 30,000 gigawatts of installed generation capacity globally. Furthermore, if we look at the power generation, fossil fuels have been a dominant fuel for generating power. This has led to concerns as the generation of power using fossil fuels lead to emission of greenhouse gases, which lead to global warming, which result in climate change, which has adverse consequences for man-made and natural systems. As a result, solutions for countering the emission of greenhouse gases have been sought. And alongside nuclear and energy efficiency, renewable energy was found to be one of the most relevant solutions for this purpose. As a result, we have seen massive uptake of renewable energy for power generation globally. As we can see, the rise has been very steep in the uptake of renewables, and by 2018, it is estimated that about 2,378 gigawatts of renewables were installed in the systems globally. Although South Africa is not a leading nation or among the leading nations globally when it comes to emissions, it is still nonetheless a formidable emitter of greenhouse gases. As we can see in terms of carbon dioxide per capita, for an example, we see that South African per capita production is far higher than that of African countries, and is also still higher than some other parts of the world. But when it comes to potential for renewables in South Africa, it is indeed very huge. It is estimated that about 280 terawatt of power reaches the land surface in South Africa. If we consider that in relation to the installed generation capacity in the country in the 2018-19 financial year, which was about 44 gigawatts, this translates to a potential of about 6,500 times what was installed at the time. Prior to 2011, there was usage of renewable energy. If we look at generation by renewable sources into the grid, there were some small hydros and large hydros. There was also a generation based on back-gas plants, which were co-fired with coal, and there were some few renewable plants for research and development by Eskom. When it comes to standalone off-grid applications, there were a few installations, mainly to power schools, clinics, and solar home systems. But all in all, the use of renewable energy for power generation was very minimal, and it was estimated to be less than 1,000 megawatts in 2011. There are several mechanisms that are available globally for stimulating the uptake of renewables. These include mechanisms such as renewable energy feed-in tariffs, renewable energy portfolio standards, and requirements or obligations which are normally set by authorities. In South Africa, the first efforts concentrated on refit, but there were some concerns after publication of the prices of these refits in terms of whether the procurement for renewable using this process will meet legality. It was thus abandoned later in 2011, and it was replaced by Renewable Energy Independent Power Producer Procurement Program. In this program, the minister will be responsible for making determinations on what energy is required. From that period till the end of March 2019, 4 determinations have been made in a series of 7 windows, and 14,725 megawatts have been determined as required. Out of that process, 6,422 megawatts have been procured and is in various stages of commissioning and operation. As we can see in the slides, we can see that various fuels or fuel sources or various renewable types have been procured, and we can see the numbers that indeed there's been significant changes from the 2011 situation. Moving forward into the future, the IRP gives us what is expected in terms of the generation mix of the country. As we can see, coal will experience a net reduction. Although there will be additions and retirements of plants, the net effect is that coal is going to reduce from the current levels of 37 gigawatts, and it will drop in net terms by about 3,785 megawatts. When it comes to renewables in terms of wind and solar, we can see that the trajectory is that of growing significance of these fuel types for power generation. Now, the incorporation of renewables into the grid does not only bring benefits. we know that benefit-wise, the fuel sources are abundant and they are clean. However, some of the properties can give problems. One of the properties is that these types of renewables, wind and solar in particular, are intermittent, and therefore, when it comes to power generation, they are unpredictable in terms of the output of generators, and they can therefore not be dispatched. Furthermore, their availability is influenced by the location, and also these sources normally connecting to the grid via converters or inverters, and that means a non-synchronous connection into the grid, which affects other properties of the power system. This can lead to challenges such as voltage rise, which can lead to damage of equipment. Quality of supply issues can arise because converters can lead to increased flicker, for an example, and harmonics, which can have impact on losses and damage of equipment. Protection could be an issue because if these sources are integrated in systems that were designed, for instance, for unidirectional power flow, reversing power flows could be an issue. Also, stability at lower level was never an issue, but incorporation of these generators at that level could be a concern. Finally, there could be issues, more issues in fact, in balancing load and generation because of intermittence and unpredictability of outputs, which can lead to more requirements in terms of reserves for properly operating the system. When it comes to network planning, the traditional approach has been to use deterministic means of planning. Basically, this involves selecting a predetermined scenarios to analyze the power system and ignore any uncertainties in states and parameters of various components of the system. Furthermore, the assumption is that the states are known and they remain constant. And the approach has been always to select the worst case scenario and plan the power system and identify problems and build network expansion based on this scenario. Obviously, there are some disadvantages with this if there is a lot of variability. Firstly, ignoring the probability of states like outages means we could be investing in states or outages that may not actually be most problematic. Also, the uncertainty in the choice of parameters means we are not certain that we have analyzed the system in its proper behavior, and the risks associated with the choice of scenarios can also not be quantified. Now, with the increase in uncertainty, this makes deterministic planning really more and more questionable as penetration levels increase. On the other hand, probabilistic planning considers the uncertainty in the operation and modeling of the power system. Basically, probability distribution functions are used to model the states and data and properties of various equipment. Once this uncertainty is modeled using probability distributions, various probabilistic computational methods like Monte Carlo simulation can be used to analyze the system. And the probabilistic output is obtained and can be analyzed, and this actually allows for a broader range analysis of scenarios and circumstances of the network. The advantage is that a better decision making can be made as more information is provided to the decision maker, and a broad range of scenarios and circumstances can be analyzed, making a more informed decision when it comes to network analysis, constraint identification, and generation of expansion plans. A related concept to planning is that of hosting capacity of networks. This basically talks to the maximum amount of distributed generation that the network can accommodate without causing constraints. When we talk about constraints, we're talking in terms of performance indices, and these can range from overvoltages, thermal overloading, quality of supply consideration, protection, and stability where it is deemed necessary to analyze. And basically, a network will have a certain level of hosting capacity. Basically, hosting capacity is dependent on the performance index. For instance, if we take thermal overloading, for an example, a network will have a certain capacity to accommodate distributed generation without thermal overloading. But once it reaches thermal overloading, we can decide to go back and say, but what can we do to expand the capacity of the network so that thermal overloading constraints are eliminated? For instance, if it's thermal overloading, we can build another line, and after that, we can then connect additional distributed generation before the constraint is reached again. That's when we start talking about enhanced hosting capacity of a network. There are several methods that have been published in literature for calculating hosting capacity. These range from rules of thumbs, which try to avoid using detailed analysis. They do consider properties of the network like the load to generation ratio, voltage regulation, short circuit capacity, to mention a few. For an example, in Spain, one of the things they consider is that the DG installed should be less than 50% of the transformer, MV transformer. Another approach to calculating hosting capacity is using analytical techniques where renewable energy is connected into the grid. Power system studies like load flows are conducted. A check is made if there are constraints, and if there are no constraints, the capacity is increased. Analysis is done again until constraints are reached, at which point we stop and we have determined the hosting capacity of the network. Another approach is what is called streamlined hosting capacity, where the hosting capacity of the network is calculated with and without diversity of the PV plants, and the curves are drawn as shown in the sketch. The second aspect involves calculating the extreme boundary and more probable performance of the PV plant or renewable, and by taking those two performances, various hosting capacity levels can be calculated as shown in the sketch. The final approach is to use stochastic hosting capacity, which utilizes the techniques as discussed previously, and they consider the uncertainty in the location and rating of the renewable energy sources, as well as the uncertainty in the load. And the outcome of this analysis is normally a range of possible hosting capacities that are calculated. In order to incorporate renewable energy in an economic manner, more and more solutions need to be considered. As we know, the traditional approach to planning is to build new lines if there are line constraints. However, we are aware that there are several problems and challenges in achieving this. For instance, we know that lines can cause aesthetic problems. There could be right-of-way issues. There could be opposition to building new lines, and there could be issues with obtaining approvals for EIAs, just to mention but a few. Another group of solutions that can be considered is compensation of lines, for instance, by using flexible AC transmission devices as an example. However, those devices don't come in cheaply. They require a lot of skill to operate, and they are not as reliable as commissioning new lines. Another group of options which has not reached a lot of favor among the practitioners and researchers is that of operating new lines, which is akin to sweating the assets. Upgrading new lines basically means you try to improve on the capacity of existing infrastructure so that you can get incremental increase in capacity of the lines. This can be achieved by changing the voltage of lines, increasing the thermal capacity of conductors, or by converting to HVDC operation. I'm going to touch on one of these technologies, which is dynamic line rating. But before I do that, we can see that when it comes to the interest in operating capacity of lines, this interest has been increasing significantly in the recent past, because as we can see from 1971 published material to 2000, the papers were few and far between. But from 2001, we can see the increase in massive interest. And I'm sure that one of the considerations is this need to integrate non-static peak demands from renewable energy sources. As I've indicated, one of the approaches of capacity upgrade is dynamic line rating. Basically, when we calculate the thermal capacity of lines in terms of static line ratings, we look at a set of weather conditions like which are wind and solar and other parameters, and then we check if the ground clearance or maximum temperature of the conductors are respected. And in this way, we calculate the rating of the lines. But this is very conservative. An alternative is to take continuous measurement in real time of various weather conditions and then derive the ampacity of the lines. In this way, we can actually also take advantage of the correlation between wind power generation and ampacity. And in this way, we can be able to transfer more power through the lines. This has got a beneficial effect because instead of rushing to build new lines, we can get incremental capacity and ensure that the economics of wind power generation is improved. In conclusion, we have seen from the presentation that the generation mix of the country is going to change dramatically, and the country is on a very steep growth trajectory for renewable energy sources. Therefore, from a planning perspective, we've got to keep checking the approaches we are using and look at other approaches and see what is appropriate so that when we plan, we can plan properly and ensure that the economics of renewable integration are improved. That also applies to expansion options. We've got to look at what can work that can reduce the need for financial investment to ensure that integration is improved in terms of economic and technological needs. That basically marks the end of my address. I think the presenters are ready and all the attendees are tuned in. I'm also waiting expectantly to hear what this great lineup of presenters is going to share with us. I wish the presenters and the attendees a great seminar. Thank you very much for your attention.
Thank you. Thanks, Dr. Mbuli. So usually the keynote address, we don't usually expect questions, but I think that was one of the most technical keynote addresses that I have seen, and thanks a lot for that because it talks to the people around the table. So I think the main sticking point here is that the probabilistic methods are now upon us, and that is something that we cannot avoid going forward to the future. Now, I thought I should just throw this example on the screen. I think it just has a lot more meaning now, looking at the situation where we are. Just let that sink. We need to remember the real power versus the reactive power and the total power. Okay, so enough about that. Now, the next presenter is Crescent Mushwana. Crescent Mushwana is a principal engineer in the Energy Center within CSIR. Crescent has a BTech Engineering, BSc Applied Sciences, Project Management Diploma, as well as the MSc Engineering. Crescent will be presenting to us the common renewables and expected behavior of common customers. Let me start from the beginning. The common renewables and expected behavior of common customer types with or without renewables. And I think this is a topic that talks to the load research more than anything else. Thank you. Crescent, I will give you a screen to take over and present. Thanks. Crescent, the screen is yours.
Chris.
And then thanks for the opportunity to be able to present the work. Just hope my screen is visible. Let me make sure.
Yes, it is visible. You can go ahead.
It's visible.
Yeah. Just
Okay.
your video is not visible.
Okay, so let me do the video. Okay. Yeah, I guess I can go ahead now.
Yes, Crescent, go ahead.
Okay, thank you. Okay, Pan, I will be presenting on common renewables. In this case, you'll see my presentation will predominantly focus on variable renewable energy sources, which are wind and solar PV, because those are the two which are really problematic, if I could use the word. And the other renewables, in terms of how we deal with them, I think they are more like common in terms of understanding their behavior. But wind and solar, they're the ones which will pose a bigger challenge. So in terms of my presentation, this will be my outline. Yeah, of course, I mean, everything that we do, especially at distribution level, I mean, my view is the energy access into Africa, it's always the biggest challenge that we are facing, to make sure that everything that we do, our expertise that we have, basically will assist us to be able to somehow manage to achieve that goal of energy access into Africa. And I will look at the global and South African context in terms of renewable energy sources, predominantly wind and solar, as I've said, and then focus on renewable energy sources, work that has been done locally, and then I'll look at the paradigm shift in terms of load versus residual load, and then also look at conservative planning approach in terms of integrating renewable energy sources versus what I would call an optimal approach. This speaks to the deterministic, in a way, versus what will be more optimal or maybe a probabilistic type of an approach if you integrate renewables. And then I will touch on a subject which, of course, will be touched on a little bit later on, why energy optimization is important for a grid planner to understand. And also look at, lastly, some of the stability issues which have been transmission concerns for a long time. And as Dr. Mbuli has highlighted, there could be some aspects now that will start to become distribution concerns as well. Yeah, so I'll just start with this slide. Basically, don't have to go too much through the text, but the most important thing here is to identify that, as was presented earlier, that electricity access or maybe energy is about economic benefits for the country. And I mean, especially for the region, all the work that is being done at a distribution level will be very critical in terms of making sure that we end up with the energy system of the future that we need. And also there'll be a lot of investment that will be required, especially in sub-Saharan Africa, for the economic growth that is required. And all of this, in my view, will be happening within a distributed level, could be within Unix, and in countries where there's no access, the solutions that will be implemented first will be solutions which are at a distribution level. So all the work that is being done in this space will be critical to make sure that energy access is achieved. And going into the future, the transformation that's expected in the countries will have to be somehow be measured. And there is a measure now that is being talked about, looking at economic power, GDP per hour, in terms of what the country is able to produce, because there is electricity access. Because in the past there've been electricity access, but very difficult for the transformation impacts to be measured. Now look at global context. I'm sure most of you might have seen this before, just to show the wind and solar resources. As you can see, in Africa, we do have like a lot of these resources, both wind and solar. And as a result, if the technologies are available to convert these resources into energy or electricity, those technologies have to be applied, and we have to make best use of the resources that we currently have. I mean, just to give an example, if you look at sub-Saharan Africa, of course, you can look at the text later, in terms of what expected in terms of electricity demand, as estimated by the IEA, by 2024, we're expecting close to around 1,300 terawatt hours per year in terms of energy. And looking at what we currently have in sub-Saharan Africa in terms of potential, in terms of wind and solar, for us to even achieve that, we will not even have used more than 5% of what we currently have. So the potential is quite huge, and we can make very, very good use of the resources in that way. In South Africa specifically, we have done some work in terms of looking at wind and solar resources. And firstly, in terms of resources by themselves, countrywide, and also looking at applications that have been done by different IPPs for EIAs. And most of the IPPs, of course, they've installed measuring devices in the different sites to check what is available. I mean, if you look at what we can be able to do in terms of IEAs, I mean, up to 90 gigawatts of PV, of wind, sorry, and 330 for gigawatts of PV, and in terms of what has been applied for. And in terms of land space, it's very interesting in South Africa, unlike many other countries where they've got like a lot of restrictions in terms of land. In South Africa, we have got vast areas which can be utilized for renewable energy integration. And work has been done in renewable energy development zones. And so far, if you look at those capacities that I've mentioned there, they are quite huge in terms of wind, 530 gigawatts, and PV 1,780 gigawatts, and roughly will be like close to around 4% of the land space in South Africa. And these capacities are huge in such a way that in our lifetime we won't be able to utilize this amount of energy. But this just shows the potential that we currently have, and that we actually have to make sure that going forward, wind and solar PV will be good resources that we can utilize way into the future, of course, as the technology cost improve. Yeah, this work, as you can see the reference, this work was done by Eskom to basically do a study to look at the cloud cover impact on solar PV output for aggregation over a large area. Yeah, so with this study, what the outcome was for the South African climate, it's been verified. I mean, a whole lot of scenarios were done to look at solar PV installations and the impact of cloud. And in terms of the PV output, the output that has been seen, if you look at the graph on the top left, in terms of the PV output, is pretty smooth if you look at aggregation over a large area. Of course, individual PV plants will have local issues which have to be dealt with. But at a national level, in terms of what the system operator sees, the PV output is quite smooth and is good for system operations. And I think currently that's what the system operator sees in terms of the PV that has been installed around the country. So basically, this just shows us that this resource is good at a national level. And if we manage to overcome the local issues, this will be good for the total system if we're aggregating over a large area. And following this study, another one was done to look at a similar work for wind. And the study for wind as well looked at, of course, in this scenario, we have put like wind plants all over the country to see what the impact is. And in terms of the results, it was something similar. And also in terms of the temporal temporal changes were very, very small if you look at aggregation over large areas. So with this study and the wind one, the work that has been done basically has been fed into the IRP, and the IRP now has got better data sets to model wind and solar for the country. That's why currently we have seen in the current IRP studies that wind and solar, basically they can be integrated at a very much higher levels because of the good data sets that we currently have. So going to the future, planning the power system, of course, will be more challenging because of renewable energy sources. And unlike the conventional power system where everything was quite predictable in terms of the demand, going forward with variable energy sources, on the demand side, there will be more challenges. So, but of course, those challenges are not without solutions. So in terms of, I'll just highlight the aspect of the residual load. Here, just showing the profiles of the different load types, residential, commercial, and industrial. And then right at the bottom also showed the profile for wind and solar. And this is like an actual profile for a day, in January 2012. And it's important to highlight that in South Africa, the general trend for wind and solar, the two are very much are highly not correlated. So wind usually picks up in the later afternoon, and we have got lots of wind in the early hours of the day, and around midday, solar always dominates. And although this one was done for the Johannesburg area, around the country, this is the type of profile that we see in South Africa, which makes the integration of the two resources complementary. And this is something that, of course, will make a big difference in terms of how much we can integrate in terms of the resources. Yeah, so if we integrate the wind and solar resources, the impact on the residential demand profile is really not that huge. But the most important thing that we can see is that all of a sudden the demand profile has got more ramping requirements. And another thing is that around midday, there is space for load to be shifted there as well. So, and this is like the trend that you see. And with this high ramping requirements, it means the other generation sources that we have to install have to be more flexible to make sure that they're able to respond to the requirements. I mean, a similar thing can be seen also for the commercial load profile. In the initial one, you will have like instances where you've got like a flat demand, but now because of wind and solar, you've got more ramps and less of flatter demand profile. And a similar thing can be seen also in the industrial load curve. So basically, this is like the trend with more and more renewables integrated into the grid, that the profiles are not as stable, and as a result, the other generation that is to complement wind and solar, a wind and solar dominated power system have to be more flexible. In other words, they'll be like having to operate quite more in terms of up and down ramps, and that's the challenge that system operators are facing all over the world. And then in this slide, I just wanted to show like the conservative approaches that have always been taken in a deterministic way in terms of how grid integration has been done. We've been looking at, if I look at A, that's where you are looking at maximum PV and maximum wind as a planning criteria, and without considering any load. And in this case, you'll have like the transformation capacity as your limitation. And then this will be very conservative, definitely. And then if you look at number B, where you consider the load, but you don't take the diversity of the generation and load into account, this won't be optimal as well in terms of planning. But this approach has been used sometimes. And then sometimes you can look at number C, if you have to look at diversity only for generation, that's for wind and PV, but the load is not included. And this as well will not be optimal. And these approaches have been used as mix and sometimes individually to integrate renewable energy plants. But going forward, looking at a probabilistic type of an approach, you'll have to look at everything combined, looking at the probabilities of planning a grid which will be able to meet all the different generation sources with wind, solar, and the load taken into account, and looking at temporal time specific probabilities which have to take everything into account. So that, I mean, in this way, you'll make sure that you don't miss any areas in terms of where you'll need to make sure that your system was well designed, and also you don't over design your system. I mean, with the current approach, like if you have to integrate wind, sometimes you'll be looking at the maximum wind capacity, and then when the PV plant comes, you look at maximum PV capacity. But if you look at everything diversified, you can be able to integrate a little bit more. Actually, with the study that we have done, we have seen that without load, even with the current system, you can be able to integrate close to around 20% more. And now when you start to consider load, you can even start to double what you can be able to integrate into the grid. And I think another study was done by Eskom, where they looked at different scenarios at the strategic level, different scenarios going to the future with a high renewable scenario, or maybe looking at conventional generation. And in terms of the grid, it was found that the grid that is required for this high renewable scenario versus the normal the conventional generation scenario, you require closely similar type of a grid, which basically shows that even with the high capacities that would be expected from wind and solar, you can still be able to utilize the grid if you plan correctly. Yeah, so this slide just shows that the other challenges that we'll have on the different sectors in terms of integrating at those levels. I'll just go through these slides quickly. Yeah, so this slide basically basically she just shows the importance of optimizing the generation component of cost. There will be another presentation coming later on today looking at IRP type of planning with renewables. This basically just shows that always when we have to integrate renewable energy sources, the generation optimization component is always the biggest in terms of costs. So that has to be done correctly upfront. And when that is done correctly, the grid basically will just facilitate the integration.
Crescent, I would like to give you just maybe a minute or 30 seconds just to put your parting shot.
It's fine.
Because, yeah.
That's fine. Yeah. No, it's okay. I'll wrap up now. Okay, and then this slide basically just shows all the power system stability challenges which have primarily been transmission focused. But now for some distribution grids, this will become aspects that we'll need to look at. It might not be everything, but definitely it's some things that now we'll start to look at a distribution level. And then these basically some of the challenges and which have been mainly transmission in the past. And some of this now we'll have to look at the distribution level as well. And this slide basically just shows that there are a number of existing technical solutions to address power system challenges. So power system stability, in my view, should never be a barrier to increasing renewable energy shares, but will be an aspect of implementing the correct strategy and costing those technical solutions as part of the overall solutions, even in documents like the IRP that we currently have, where some of these have not yet been done. But if this is done correctly, these solutions can be implemented and a lot of more renewables can be integrated into the grid. Yeah, so this is my last slide. Thank you.
Right. Thanks, Crescent. Yeah, very, very informative. And I see that there are questions as well. So as we have mentioned, colleagues, questions will be will be sent to the presenters, and they will be attached to the broadcast that you will get on our platforms. Right now, we are pretty much going to take, I think it's going to be a 2 minutes break right now to move over to the next session. And the next session is titled Overview of Policy and Regulation Guidelines. So it's starting at 9:55, which is like 2 minutes away from now. Please do take a leg stretch and we will convene again in 2 minutes. Thank you. Thanks, everyone. Okay, welcome back, everyone. I see now it's time to start the next session. And as I indicated some 2 minutes ago, this session will be chaired by Lloyd Setlhogo, who is our Load Research Chapter Secretariat. Lloyd, over to you.
Good morning, ladies and gentlemen. Greetings. Welcome back. Mings, can I ask you to confirm whether I'm audible enough?
Yes, you are, Lloyd. Go ahead.
Welcome, ladies and gentlemen. My name is Lloyd Setlhogo. I'll be chairing this session. So the next presentation will be done by Faure van Schalkwyk. Faure, he's the head of our solar training center, cybernetics. He has a BSc engineering and also MSc in engineering. Nicholas Faure van Schalkwyk is an electrical engineer by profession, and he's also done a lot of work in the area of solar PV environment, particularly in public and private sector. He's managing also a company that is offering solar PV training and technical support for installers, as well as for municipal or government officials. So without further ado, so that I don't waste time, I'll then hand over to Faure van Schalkwyk to do his presentation. Faure, if you are ready, please take over. I can see your screen.
Great,
Your
thank
screen
you,
is
Lloyd.
clear. I can see your webcam also.
Perfect. If the internet's not good, you can just switch off the webcam. Perfect. Okay, great. Thank you. Thank you, Lloyd, and good morning, everyone. Thank you for the presenters and for SAIEE for having me today. The topic that I need to discuss is not a very exciting topic. We know when it comes to standards and regulations, it can be quite boring. So I'll try to keep it as short and as interesting as possible. But before I start, I think we just need to have a little bit of an analogy to understand the reason of why do we have standards? Why do we have regulations? And essentially, we have regulations and standards in place so that it's fair, so that it can be sustainable, and also to make sure that it is safe. And I think that is a key aspect area that we need to keep in mind. And if you think about playing a sport, there are rules in the game. And we need to adhere to the rules to achieve those outcomes. And this is the same when it comes to renewable energy. So what we will discuss today is we'll start with the IRP 2010. Dr. Mbuli pointed out to that just to see the context of where our government is committed to in terms of renewables. And then we will look at the applicable legislation with key focus on distributed generation or better generation, which is closer to the consumer. We look at the elements of a municipal SECG process or small-scale embedded generation. At this stage, municipalities are the guardians and the custodians of enforcing regulations and specifications or standards. The SANS 10142-1-2, the specific requirements for embedded generation, which is still a draft form. I'll give you a little bit of an update on that. And then we will, when we blow the whistle at full time, we'll just give you a few summary points to take home. So as Dr. Mbuli pointed out, he was referring to the Renewable Energy Program. And if we look at the IRP or the Integrated Resource Plan, which is the government's commitment or planning for the next 20 to 30 years to say, what forms of renewables are we going to install and how does our energy mix look like on the long run? And as we can see that there is a big portion of new allocation for PV and wind, and also for the distribution side that comes into play. Now, keep in mind, for these big plants, for these large allocation, it all falls under the Renewable Energy Program. There is a bidding process in place. The rules are a little bit different, and my focus will be to focus on the distribution or the SSEG side when it comes to rules and regulations. So to summarize the new renewable energies we're looking at, we can see that there's a large portion allocated as presented by the previous presenters. And again, a very large proportion attributed to distribution generation. And that is the area which I would like to spend more time on in terms of regulations. So what are the applicable legislation when it comes to renewable energy, and especially on a distribution level? So if you look at the picture, we've got our energy source. It could be PV panels, an inverter, the meter, and then the utility. So there are some legislation applicable to the utility side, and then there's on the property or the installer side. So on the utility side, we know we have the OSH Act, and the OSH Act specifies the safety of staff. It's essentially to protect the staff and make sure that they are safe. And this is then supported by the electrical machineries regulations and the electrical installation regulations as well. Then there's the ERA, or the Electricity Regulations Act. And under this act, it stipulates what are the requirements and what should be done in terms of having a generation license and then a distribution license in cases where, like municipalities where they distribute electricity. They also have the distribution grid code, and then there are some small-scale electricity generation regulations that also applies. Coming a little bit closer to home to the actual installation, again, the OSH Act requires safety of installations, which covers the electrical installation regulations. This is also the regulation that stipulates, for example, that all electrical work has to be done under a registered person, under the supervision and control of such a registered person. We've got the wiring code, which we know is the Bible for electricians doing installation, which is the SANS 1142 Part 1. And then Part 2, which is then obviously in development, which I will talk about just now. And then there has to be a COC for all electrical installations, including solar PV or renewables for that matter. Okay, we've got the Electricity Regulations Act that also specify what are the generation license requirements. As you know, in Schedule 2, there has been an exemption that no license is required for up to 1 megawatt. And in the past, there was a registration required for up to a megawatt. That has changed now. So NERSA requires only systems above 100 kilowatts to be registered with them. Below that, that needs to be registered and the information needs to be captured at municipal level. Either way, the generation license requirements are supported by the Schedule 2 of the ERA. Then we know that NERSA also has certain rules in terms of registering the system or getting the license. And they are also playing an active role the past few months actually to specify what are the tariffs for SECG so that we can export electricity and get some benefit from that. We also have utility electricity bylaws that enforces NRS specifications. It's not required by law nationally, but it can be enforced by a bylaw when municipalities adopt these specifications to say, this is our requirements when it comes to embedded generation. And I will give a brief overview of that as well. So visually, let's just see where does this legislation fit in. So here we've got our energy source feeding into the distribution board. We've got our loads, and then we've got the grid connection. So if we look at the NRS 097-2-1, it is actually a utility interface specification. Some understand it as an inverter specification or certification, but it's actually to say whatever form of EG you have, if it's solar, wind, whatever it is, if it interconnects to the utility, that it has to comply to the 2-1. Then we've got the SANS 10142, which refers to the actual physical installation of the installation. The existing SANS does cover some solar PV aspects or renewable energy aspects, but the updated version of the -2 goes much more deeper into the embedded generation side of these type of systems. And then we've got the NRS 097-2-3, which looks at the utility side to make sure that the utility capacity is large enough to handle the solar PV system and that it will address the main concerns as listed by our previous presenters as indicated. If we look at the municipal SSG process elements, you need to understand that at this stage, municipalities are at the forefront of making sure that the system complies, that it is safe, and that it's done properly. And I'm not going to go through all of these blocks, but essentially, these are the building blocks that municipalities put into place and which we assist them with the funding from GIZ, support from SALGA and DMRE, to get their requirements, the application process, and the assessing of application in place so that they can allow SECG to be installed and manage it in a sustainable way. We do still offer this training to municipal officials and any delegate that's actively involved with realizing SECG on distribution level. Okay, so looking at the NRS 097-2-1, there are a few things. It's a summary of what it is about, right? So the first thing is, what is the system to be expected? So there's certain parameters or certain things that will happen from the grid side, and your inverter or your SECG needs to be able to handle that and continue producing power. The second one is what is allowed. So when it does produce power, there's certain power quality parameters that needs to be achieved. Like Dr. Mbuli pointed out, that if these things are not in control, it could have a power quality issue. And then the last thing is, what should it do at certain conditions? For example, if the grid goes off, it has to switch off and not feed back. That's where the whole concept of anti-islanding comes in, to prevent it from reducing power when power is off. And that is why, if you look at the 2-1, it is actually a safety mechanism to make sure that the installation is safe and to make sure that it complies and will work with the utility and not against the utility. We're all aware of City of Cape Town that has an approved inverter list that you can go to. There's obviously a difference between the 2010 and the 2017 version. I mean, the key difference there is the EMC requirements, and that is definitely a big challenge for municipalities. Oh, sorry, so for inverter manufacturers to catch up with the 2017 certification. We are of the view that the 2010 version would still be acceptable, as long as you have your processes in place, that when you do enforce the 2017 requirement, that there was ample time to make the amendments as required. If we look at the NRS 097-2-3, it's a simplified connection criteria. Now, just to understand, not all municipalities has the capacity or means to do a detailed grid impact study. So the 2-3 is an easy way or quick way to see, will we be able to connect the system, and to a large extent the network will be able to handle that. So that's why it's known or referred to as a simplified connection criteria. There's actually a flow chart that you have to go through step by step, so it guides you to go through the steps. And then there's some basic checks to make sure that you're within the correct percentages of certain parameters. If you do not meet these basic checks, it will go over to a detailed grid impact study. You keep in mind, the 2-3 is limited to low voltage. It's also limited to system size of 350 kVA before you have to go to the next application. I like to show this picture because it's a nice summary of the 2-3. So what we have here, we've got our LV network and our MV network. On the LV side, we've got a shared feeder, which is typically like residential. And then on the LV side, we also have our dedicated feeders, which is commercial and industrial. And this is where the whole concept of the 25% comes in for residential, and the 75% limitation on your NMD or your main circuit breaker size in terms of the EG that you can install. Now, as the standard is specified, this refers to the EG size, but I do know that there are some municipalities that says they allow this in the context of how much you can export. So there are some discrepancies, but as the standard stands, it's with the size of the EG. And then going upstream, we will also look at a medium voltage side to make sure that the total EG, if we add up all the embedded generation, all the forms of renewable energy that's embedded to the grid and grid connected, needs to be less than 15% of the MV the MV feeder peak load, and we need to make sure it's smaller than the 75% of the MV LV transformer rating. Okay, going into the SANS 10142-1-2. So first of all, it's situated at the Department of Labor. They are the custodian of this document, and it's enabled by the OSH Act. It's obviously supported by the electrical installation regulations, and it mainly, at this stage, it mainly covers grid connected, embedded generation or distributed generation systems. When we look at hybrid systems or island systems, there's still a lot of room to grow. But we had the approach to say, let's apply the parentis theory. Most of the systems are grid tied, and that's why we want to get the standard out as soon as possible. Now, just to give you a quick update, the document did go out for public comment. We did get a lot of feedback, which just shows you that there's a lot of interest from the industry to get this thing out. We had like 70 pages of comments that we have to process. We already had 2 workshops, SAB workshops to process those comments, and we have another one this Thursday. So once that is done, the chances are that it will go out for public comment again because of the big changes that we have to make. And then afterwards, we'll adapt the comments and then it will be published. According to SABS, we're looking at another 4 months. So my take is that end of the year, hopefully it will be finalized and published. In the meantime, there's a few other things to consider, which is optional quality assurance initiatives, which is known as the PV Green Card, endorsed and supported by SAPIA, and then the P4 that's supported and initiated by RF. So while we wait for the standards to come in place, there are other mechanisms which is totally voluntary, optional, so that customers, installers, and utilities would know, listen, this is someone that has some form of proof or some form of leverage on these people when it comes to doing quality and safe installations. Okay, so yeah, a few points to remember. I think the first thing is that legislation for renewable energy does exist. They are there, and some of them are very inhibiting. Some of them are very difficult, but we need to realize it's the rules of the game. So if we want to make sure that it's fair, that it's sustainable, and that it's safe, we have to play according to the rules of the game. And if we want to score and win the game and move forward, we have to play again according to the rules. And that's why we have to, even if the rules are not always fair to our side or as an installer, as a consultant, we still need to make sure that we make provision for that. Standards and regulations are there to protect both the customer and the utility. I think when we look at the regulations or standards, we tend to look only, focused from the one side to say, well, it's only focused to the utility, they're not worried about the customer, or the other way around. Whereas we need to look at the holistic setup, which means we need to understand that things like the 25 and the 75% rule with the NRS 2-3 is not because municipalities are difficult or preventing it to happen. It's just because they want to make sure the network is protected and the network can handle it. So, and to make provision for future connections so that the customer next door can also connect. So we have to be aware that it is applicable both sides. New regulations and standards for renewables are in progress. For example, the SAN standard. We also know that there's a hard push to exempt licensing requirements for up to 10 megawatts. We know that the government, if you look at the RP, committed overall, and even the president indicated that we will have much more allow embedded generation and business to generate their own electricity. But we need it. We need the commitment on paper. We need it in the form of standards. We need it in the forms of acts and laws, and not just a policy. And we hope to see that coming soon. And like I've indicated in the interim, there are some solutions that we can use, because just to give you an idea, the SANS 10142-1-2 was in development the past 5+ years. And by the time this thing has been published, the technology has changed already. So we cannot wait for these things. I hope that we can find mechanisms to have these regulations and standards updated much quicker and sooner. If you think about the IRP 4.0, fortunately, COVID, delayed it in the whole process. But it's still, we need to have fast, quick ways, and something like the PV Green Card or the P4 test or industry-driven quality assurance initiatives is a way to make sure we apply international best practice and make sure it's safe until the standards are in place. Okay, and that is from me. I've highlighted the key points. If there's any questions, please ask. I would like to respond with the time that if there's time available.
All right. Thank you, Nicholas, for this wonderful presentation. You have done very well when it comes to time. Colleagues, in the interest of time, I see it's 10:15 now, because we need to shoot to the next presenter. Please, if you do have any questions, please put it on the chat group. But maybe I can be generous enough to take one question, but maybe not, because already time is over. Please just post your questions on the chat box. We will come back to you. Our next presentation is Avinash Ramdhin, and he will be talking to us about the renewables planning benchmarks and guidelines, looking at the perspective of Eskom. So Avinash is a senior engineer, smart grids in Eskom. He is holding a BSc engineering and also MSc in engineering. So Avinash, I'm not going to waste much of your time. So really, please take us through your presentation so that we can be able to benefit also from this presentation you're going to give to us. Over to you.
All right, good morning, everyone. Thank you so much. Today I'm discussing on the renewable guidelines and renewable energy that planning in Eskom has looked and dealt with in the last few years. A presentation overview is looking at some generator types, some technical issues with DG integration, mitigating steps for the DG impact onto our networks, standards overview, and some of the Eskom planning standards and guidelines, as well as the hot topic of SSEG at the moment. Okay, so basically with the staggering electrical growth that we have been seeing, customers are moving towards renewable energy as a new source of energy to power everything that they need to. Obviously, that's constrained within the type of load that they have. And then with Eskom planning, doing network development plans, there needs to be some form of integration between distributed generation and network development plans. And therefore, the planning fraternity has put together guidelines and standards in order to take control of that new technology. Okay, so some of the generator types that I'm just going to talk about briefly are rotating machines, which incorporate steam turbines, gas turbines, rotating machines as induction generators, and obviously the last one, which is DC current sources as photovoltaics. Just a few differences between synchronous generators and asynchronous generators. Synchronous generators can inject or absorb reactive power, which make them much more expensive rotating machines. Asynchronous generators absorb the reactive power, and some of the most important aspect there is the short circuit contribution, which takes longer to decay in synchronous generators because of the subtransient parameters defined in an actual machine. Okay, so in the planning studies for DG integration, some of the studies that are required to be performed by the planning engineer are load flow studies, fault levels, thermal loadings, voltage levels, which is voltage rise, rapid voltage change, and obviously incremental fault levels as well. Now, these obviously depend on the characteristics of the generator, the actual size of the gen, and the location of the generator onto the particular network, whether it's MV or HV. So in this illustration here, we just look at a MV feeder line. As you can see, during light loaded conditions, the voltage profile picks up quite a bit when you have a generator onto the network. And obviously, this profile is dependent on the location of the generator. Okay, so some of the maximum generation minimum load, this is the fault level in which it distributed along in 11 kV feeder. As you can see, it starts off very strong at the source and then it tapers off towards the end. Obviously, generation picks up the fault level quite a bit depending on the type of machine or the type of inverter connected to that network. Some of the electrical factors affecting grid connection. So the most important parameter on grid connection is the XT double prime, which is the positive sequence impedance for synchronous machines. For the typical PV installation, in the past we've been using 1 to 1.2 times the power rating to model these generators, but we can almost negligibly ignore that setting now, with the technology improvement in inverters at the moment. Voltage rise is also a critical issue for networks with multiple connected generation. We see a lot of voltage rise at different points in the network, and we need to mitigate that. And then, as explained, rapid voltage change is the steady state voltage that is settled once you have a disturbance on the system. So for fluctuating generation such as solar and wind, because of its intermittent variability, is defined as less than 3%. And for non-fluctuating, example, synchronous machines, etc., is 5%. Transient stability is not normally an issue with distribution systems. It is an issue with large magnitudes of generation on transmission systems, as well as weak distribution systems. But on typical distribution systems, the fault level is strong enough to accommodate that. And then obviously in planning, we don't look at the power quality issues in detail unless the IPP has been approved and is going ahead. Harmonics do are analyzed and they are created with saturation in the machines or by other power electronic equipment connected on the same network. Okay, so just looking at a bit of voltage rise and as penetration of DG increases. So as you can see, this is a medium voltage network. The red squares are PV installations, and these scenarios are becoming very typical in our current situation. As you can see, the voltage profile, the PV does pick up the end of the line depending on the location of the actual generation. As you add more generation to this network, which is also another typical scenario that we are experiencing, the PV penetration does increase quite a bit and eventually pushes the profile past the 1.06 limit or standard limit that is set for us. And then obviously voltage mitigation needs to, high-rise voltage mitigation needs to take place at that particular point. You do have an issue with cloud cover, as Crescent mentioned earlier. The study that was performed did indicate that cloud cover that caused a greater than an equivalent or greater than a 3% difference in voltage does give you flicker with adjacent load connected in proximity to the existing PV networks. In terms of the factors affecting the transient stability of the actual generator, the critical clearing time is the actual time that determines whether the generator goes onto stability or whether it becomes unstable. For synchronous machines, pole slipping is a very common stability criteria. A sudden connection disconnection of a generator, especially if it's supplying bulk load or load greater than the actual generator itself. And then to improve some of the stability issues, we look at reduction of network line reactance, clearing that particular fault as quickly as possible. And the most common legacy method is to strip the generator. Now, previously there was a study done where different network strengths were looked at. So, for example, if a grid strength of 1 to 5 kA was, which the gen has been connected to, if a volt drop of 3% occurred, the generator or the grid strength needed to be 2.9 or 3 times the strength of the actual machine for instability not to occur. So this study also states that even if there's a 5% volt drop that is looked at, then the grid strength needs to be at least twice that of the machine fault contribution. Okay, so some of the mitigating impacts to networks, thermal loading after gen connection, retemplating the line is a critical, most cost-effective issue. Installing large conductors, which is not a cost-effective solution. Constructing another line of cable as an alternate feed could also help. Upgrading the existing transformers for a decrease in impedance would help. Connecting embedded generators at a higher voltage level, which is also a preferred mechanism for this, and reconfiguring the network for the impedance drop. So voltage rise and voltage drop has to be kept within limits, and in order to achieve this, we can achieve reactive power compensation by changing the generator control mode. The generator will absorb reactive power, so the generator acts as an inductor to reduce the voltage rise on the network, and you can coordinate the voltage control through on-load tap changing, curtailing the generator's output. That is typically done via droop control, upgrading conductor sizes and connected to higher voltage levels. The fault level increase after connection of the generator can be mitigated by upgrading existing equipment, creating open points, and using high impedance transformers or series reactors. Okay, so some of the standards that apply to renewable energy and to in the planning space, that is currently being used to analyze the integration of DG into the network. So it's the NRS 097-2-1-3. I think Faure also took us through those standards. The NRS 048, which is the limits on regulation for MV and LV. The apportionment standard, which is the Eskom standard, the NERSA grid code, and the renewable plant grid code version 2.9. Now, and then we're using the planning standards for shunt compensation, for grid connection, and the interconnection standard, which is our protection guideline. So the protection guideline states that every distributor needs to have a connection. The grid code states that every distributor has to have a guideline for embedded generator connection and the protection thereof. These are some of the protection functionalities that are stated in the guideline 34.17.65. This protection functionality is required at the point of common coupling and the point of utility connection. And these are some of the terminology I would use. The common coupling is when other customers are connected to the same bus bar. Utility connection is when the actual EG connects to the Eskom system, and the PGC is the actual generator connection point. So the legal requirements and boundaries of accountability, all EG operators greater than 1 megawatt require a license from the regulator. The DX is responsible for protecting the network, and the utility is held for all quality of supply issues that for any integration connection. The protection that is applied at the point of utility connection. No cogen is to support an island, and the cogen is responsible for protecting and controlling the generator and cannot energize a dead network. Okay, so, some of the connection types. Connection 1 is direct connection to an overhead line. Connection 2 is a connection to a HV bus bar. Okay, and then the connection 3 is a separated plant that sits somewhere else that is connected by a high voltage interconnecting line. So those are 3 common types used in analyzing planning criteria. Okay, so some of the SSEGs, which is the current technology that we're looking at the moment. Some of the standards that were spoken about is the NRS 097-2-1 and -2-3. Faure also spoke about the SANS 10142-1-2. The categories in the renewable power plant code talks about category A. This SSEG falls under category A, A1 to A3. Yes, okay, so Faure spoke about the utility interface and the simplified criteria. Now, because he has spoken about the simplified criteria, I'm actually going to jump to the actual criteria, which is limited to 350 kVA for low voltage connected generators. Eskom, what they have done is they've actually used or have came up with other guidelines in which to further simplify those criteria. Some of the guidelines here is the maximum generation limits on LV networks, the framework design solutions for customer-owned SSEG and the commissioning standards, as well as compliance certificate and B-trade. Okay, so the new generation limits that were redefined from the NRS 097-2-3, they basically incorporate the boundaries that are looked at in terms of the 25% NMD and the 75% of the NMD for dedicated feeders. The total generation connected to a medium voltage network, as mentioned previously, was 50% of the MV feeder peak loading. These particular parameters of 097-2-3 were used as the basis for calculations to further simplify criteria that is used for LV generation, and it is a new standard in Eskom as well. This table basically summarizes these values. So, for example, in a system or a residential unit that has customers with 40 amp breakers, 1.5 kilowatts is the maximum single phase PV that can be connected to their rooftop, for example. And then for 3-phase, if they have an 80 amp breaker, it's obviously times 3, so 9 kilowatts to be the maximum generation that it can be connected with the 80 amp breaker for that residential customer. Okay, so the DGSL is the protective device that is used for SSEG connections. This is a device that is meant for particular safety. It is installed between the actual customer's inverter and PV installation and between the Eskom and the customer. So this device is an automatic device. So if there's no power on the Eskom side, this device will kick off the inverter. There's still a debate on the hybrid functionality of inverters, which are not legal at the moment. So some of the connection types, which I'll go through very quickly, is for example, in a cable situation, you have a customer isolation point and the DGSL between the inverter and the customer DB. You have in a shared overhead line, you have the DGSL installed between the inverter and the customer's DB. It's particularly used for shared LV. The Dekenah safety lock is also installed in cable networks because the isolation point is taken to be on the metering kiosk and the RMU. On dedicated LV supplies, typically the customer isolation point was first installed before the advent of the DGSL, and the two are required technologies in order for this to work properly. In terms of the category A3 SEG within Eskom MV cable, the MV isolation point and the DGSL also are used in this cable network. The isolation point can either be an RMU or a mini sub. Okay, so in the final closings is that a PPA, how can IPPs get money back into the grid? They can do so through a DOE procurement program by the renewable energy or baseload PP. Wheeling to third party between parties, between two other parties that can exist anywhere else into the grid. They can bank the energy across a 12-month period, and they can use it for their own use. And if they use it for their own use, it's not regarded as an exporter as long as they're not synchronized to the grid. And in all the cases, a grid connection has to be authorized by the distributor as a legal agreement. And if they're greater than 1 megawatt, they require a license by NERSA. Between 100 kilowatts to a megawatt, they require to be registered. Now, this commercial options supports the future DSO for distribution. Okay, so in closing, all the documentation that was discussed, there were brief points that were discussed in the planning criteria. And as the documentation of technical aspects increase, it enables better planning, better projection, and better modeling of the EG plants as we go into the future. There are structured work groups to facilitate these standards and guidelines for implementation, and DER is a key factor in the evolution to smart grids. Okay, thank you.
Thank you, Avinash, for this important and very informative presentation. Avinash, I sincerely want to apologize on behalf of our committee and the organizers, because the holding slide that we have shown there, I think it was mixing your bio with the bio of Nicholas. So we sincerely want to apologize. Please, we're sorry about that. Our next presentation, when I look at time, we're still. All right, thank you, man. Wonderful. That was a very wonderful and powerful presentation about the legal requirements and guidelines for Eskom. I think we need that. So now we are going to go to our next presentation, which will be done by Ismail Jefferies. Ismail is the head of service connection planning at the City of Cape Town. He's holding an MTech in electrical engineering. Ismail, your job there at City of Cape Town, yeah, I don't really want to be in your shoes. So as the head of the service connection planning there, managing that division, looking at all these requirements in terms of the connections there on the municipality, City of Cape Town, with what is happening there, yeah. Let me give over to you, Ismail, so that I don't take much of your time. Over to you when you're ready.
Thank you, Mr. Tse. Good morning, everybody. Yes, from the City of Cape Town side, I will be presenting how we deal with our applications process for the connection of renewables, as well as with the main aspect of the customer involvement, and as well as our challenges with some of the technical compliance issues that we are experiencing. So moving forward, Yes, so I'll be covering the SACG requirements. This is a document that we have available.
Ismail, sorry
I
to
will also
interrupt.
yes.
Sorry to interrupt. I'm not sure. I can't see your screen. I'm not sure whether is it on my side. Mix, can you confirm that we can see Ismail's screen?
No, we can't. We're waiting for Ismail to accept that he needs to share his screen. There we go.
Okay, there you go. Thank you. Thank you. Over to you, Ismail. Can continue.
Okay, thank you. So yes, I'll be covering the SACG requirements, our assessment procedure, some challenges that we are experiencing in the category A3 and B installations, our registering process, our results of the awareness campaign, and what we do moving forward. So in terms of the SACG requirement document, it's a live document which we have on the website, and it basically spells out the requirements for customers to have their PV connected in terms of residential and commercial requirements. It basically indicates the generating limits that we have, the metering options and tariffs, relevant standards, and more information on our approved inverters, as well as the professional sign-off requirements. On the professional sign-off requirements, customers are currently very upset with us due to the high cost of this requirement, but we unfortunately still insist on it due to the SENS 10142 wiring code document being silent on the grid code compliance, as well as the NRS 097-2-1 specification requirements, specifically, or some of it, for example, the islanding test, the protection and the generation of the capacity settings, as well as the reverse flow blocking protection. So as Faure indicated, the draft SENS 10142-1-2 is out for comments, and we were hoping that this document would eliminate the need of the professional sign-off, at least maybe for the residential customers. However, as you know, the document is currently in draft format, and it doesn't unfortunately address the requirement in terms of the COC. It basically indicates that a professional registration number is required, but where applicable in the section 8. So it doesn't specify if that is a engineer, technician, technologist that is required, or electrician that needs to sign off. So we as the city did comment on that to try and get that resolved, because that will also eliminate this need for the pure sign off, and customers would obviously be very happy about that. Then in terms of our assessment process, the main considerations, we do nothing fancy. We're basically following the NRS 097-2-3 simplified method. Yes, we know it's limited to the 350. After that, we do some network engineering studies. And then for the bigger installations greater than 30 kVA, the CDD requirement in terms of the NRS 097-2-1 has always been a hot topic from customers who try and comply with it, where there are multiple inverters installed to ensure that there is a CDD that's able to basically disconnect all those inverters at once. And the greater than 100 kVA grid code requirement in terms of the controls and the signals. And yes, obviously we all know that any installations greater than 1 MVA require a license from the regulator. So in terms of the grid impact studies, my screen doesn't show the so unfortunately my screen doesn't show the picture now, but basically we have with GIZ and with MPE, there is a guideline that they have basically come up with, which basically allows for a 1% voltage rise in each section of the network And this guideline is very much similar to the simplified method. However, it also allows you to basically go up to MV installations in terms of calculating the hosting capacity. And basically, you calculate the voltage rise in a section of the feeder, for example, across the transformer. With that voltage rise, you basically determine the current and then the maximum power, and that becomes your hosting power. So it's a very simplified method. You simply just use Ohm's law, and you can do it via hand calculation to determine your hosting capacity of the network. So we're hoping that with the assistance of CSIR also involved with this, that hopefully moving forward becomes the national standard. The benefits of that system basically caters for the LV and the MV. As I've indicated, you can even supply it up to 5 MVA. And the outcome of those studies is evaluated in terms of the quality of supply standards, NRS 048. In terms of our generation limits, sorry, I must just get the correct slide here. So this is what I was referring to. Apologies for that slide there. In terms of the GIS and MPE guideline that we've come up in terms of the hosting limits. And then in terms of our generation limits and categories, this is where we have a lot of problems with customers. So what we have done recently, we need to update our SSRG requirements with these recent developments that we've basically agreed on within the various departments of the City of Cape Town. We have basically categorized now the categories. We've come up with 4 categories. A and B in this case is the grid-tied and the grid-tied with the hybrid. There are not so much problems with this one. However, for example, a customer residential have the option to apply not to export, therefore his meter doesn't get changed, and he applies for grid tied, and in this case he needs to basically have reverse flow blocking, and the PRN sign off that installation as compliant, yet we then find that the meter is spinning back. So how we circumvent that is, for example, now by installing a PPM meter, and then unfortunately the customer pays for what is generating. But in that way, the customer would then certainly ensure that the reverse flow blocking gets installed by the installer, and therefore then have a compliant system. So with category A and B, we don't have too much problems. The maximum generating capacity still remains also in terms of the limits of the 25% of the NMD. Category C, it used to be off-grid, but we now call it standby. And the reason for that, it is still interconnected with the electrical installation via changeover suites. And with the passive standby, UPS utilizes an off-grid hybrid system. And the type 2, the alternative systems, this is where we get most of the problems, because customers from a single line diagram perspective indicates that the systems is off-grid, but technically it is a grid-tied system. So we're now trying to just make this more clear. And in this case, for example, in terms of our application process, the customer basically just submits a declaration, no PRNs is required. And what makes this also lucrative for customers is that they don't need an approved inverter. because it's not really parallel to the network. It needs to basically, it's either or with the changeover switch. So what we're allowing here is no battery capacity limits. However, if you charge the battery from the network, it's limited to the 25% of the customer circuit breaker. And the maximum inverter capacity, we will basically also limit according to the customer service breaker size. And that is, for example, for a 60 amp single phase customer, that would be the 13.8 kVA inverted in. Then category D, no problems there. That is the complete off-grid system where it's physically separated and electrically not interconnected with the installation. And there, obviously, there are no limits for that one. Then in terms of the tables, our table 1 currently we will update, where we will now indicate the maximum inverter capacity, as I've discussed now with the categories, as well as the limits in terms of the battery charging currents. As you can see there, for example, for a 60 amp, it will be 15 amps where the charging current will be limited to in the case of a hybrid system. Just to indicate you from our database how the off-grid, or what we call now the standby systems, are basically almost overtaking the grid-tied installation. So we're now sitting with almost 70% of off-grid installations compared to grid-tied installations. And this is, like I said, because we don't need that approved inverter, and the customers don't need the PRNs, and most of the customers is going for this type of installations. This on this system also is that because there's also no, let me first just go on. In terms of the challenges that we're experiencing in terms of this A3 and B category, A3 is basically from the 100 kVA to 1 MVA. In terms of the grid code, we need to ensure the control functions for the absolute power production and the power gradient. Now, this becomes very difficult in estates with bulk point supplies, where we as the city only obviously then take the body corporate as the customer. The individual residents with private metering is not really our customers. So the body corporate needs to ensure that this installation complies. And most of the time, technically, we can get compliance. But it's obviously just from a practical perspective where it can become problematic due to the existing installations where provision was not made for these controls. Most of the time you can get away with fiber. However, because fiber is not reliant, you would need copper cables to the individual units in order to comply and to have a safe, proof system. And that is actually where we start struggling with customers to try and ensure that they get these systems in and that would be reliable. On the MV side, we're getting now customers applying for greater than 1 MV installations. We've got 5 applications thus far. These are existing customers with 1 MVA embedded generation already installed, and they simply just basically want to increase. Now, this category B is quite a big category, from 1 MVA to 20 MVA. Our part 1 in terms of the NRS is still in the draft version. It's not approved. The Eskom one is very similar to the draft. These installations does basically only cater for big MV installations where either you connected via gen transformer onto the MV bus, or directly from an MV onto the MV bus. Now, it doesn't cater for existing customers with, for example, a smaller 5 MVA customer with existing 1 MVA wants to increase to 2 or 3 MVA SSEG that's embedded in the LV network already. In that case, these documents doesn't really talk to such type of installations, and we're now working on quasi solutions to be able to actually facilitate it for customers. So that is also something that we currently hope to resolve. On the registering of systems, just before COVID, 26th of March, the government notice 402 in terms of registration requirements. So now this latest one indicates that customers under 100 kilowatts needs to register with the distributor. Then section 3 indicates that up to 1 MVA needs to register with the regulator. So that is a concern in the sense that they obviously still needs to apply to the local municipality to get approval. So at what stage do they register with the regulator? That is something we would need to take up with NERSA. In terms of our snapshot for the database, so far at the end of July, we had 358 installations and a total of 82 MVA, but this is now all installations in various stages of statuses, from an application received where the staff is still busy with it, illegal installations that's being legalized, and also approved installations. So it is the various statuses. For only the grid-tied approved installations, we're looking at just over in total between residential and commercial, just over 1,000 installations on our network currently. And the capacity for that is 43 MVA in total. In terms of our awareness campaign, we were basically driving this campaign during the June 2018 and 19 financial year. It was intended for 6 months. We ended up for a whole year. And basically what we were trying to achieve here is bring the message home in terms of compliance with the law, safety of installations and staff and public, as well as the quality of supply issues and the network issues to customers. So we've been using extensive media campaigns to advise customers of this. The campaign was quite a success. As you can see, at June 2018, we had 404 applications at that time. And at the end of June, we had 3 times that number, which was a good success. However, it also caused a big backlog for the staff to manage through all those applications. Moving forward, post our awareness campaign, PV is unfortunately not something that the customers can hide. It's quite visible. So we do serve aerial survey, and we have done this recently, where basically we are then able to identify all installations from the aerial photograph. We then move that information into a spreadsheet where we compare that with our database in terms of the applications that we've received. And then unfortunately, we saw that 50% of the database is illegal installations. So how do we deal with that moving forward? So 2 ways. Some of the registered PV installations, unfortunately, we have installations that's been with us since 2014, never been concluded. Customer just applied. System is up and running, but never been concluded. So we now introduced a cutoff point where we allow only for them to basically provide us with the details within 3 months, so that we can conclude those systems. If not, we then would deem them illegal. And we ensure that the PPM meter is being installed at that installation. That is for the registered PV installation. For the unregistered, we basically issue them a contravention notice. We get them to pay a service fee, and then we notify them to register within a month. And if they don't do that, we then unfortunately, in terms of the bylaw, will disconnect their supply to the property. Just there right at the bottom, as you can see, we've basically had at that time from the database 88 large commercial illegal customers, 404 medium commercial customers, and 1,900 small residential customers. So we're still busy with this process. Customers
Sorry,
is quite still upset.
You are left with just below 30 seconds. If you can wrap up, please. Thank you.
That's fine. I'm wrapping up now. So we're busy dealing with those customers, and we're dealing with them to try and ensure that they basically get legal and being compliant. Moving forward, we basically just need the SANS 507 documents to be updated in terms of the ADMD with the new energy efficiency lighting, as well as new heating and cooling technologies. The ADMD is no longer what it used to be in terms of the old ADMDs that we've used. So we really need an update so that we can also determine what the PV, the impact on it, and how that impacts onto the network. Then in terms of that NRS 097 document for the MV and the HV, we need an update on that. And then from what we're doing, that's from industry side. What we're doing from the city side, we will be updating our SSCG requirements in terms of those new categories. We definitely want to resolve the issues with the PRF sign-off, the professional sign-off, trying to resolve the metering, the cost of it, because that's quite still a complaint from customers, and then trying to improve our turnaround time with these SSG applications. We would like to hopefully in the future go to this online application process where we would be able to automatically provide customers with reference numbers and tracking their application through the process. In terms of the SSC data being on our GIS system, it is currently being loaded there, but a lot more needs to be done in terms of, for example, indicate on which phases are the customers so that we are be able to do proper detailed engineering studies, because with the unbalance of the PVs, that can also cause less customers to be connected. So if we can get that right, we will be able to ensure that more customers are connected. And that is it from me. Thank you.
Thank you very much, Ismail. Unfortunately, again, we are behind time, so we will not be able to take any question. But please, colleagues, just post your questions on the chat box, and then we are going to go for a break. But as we go for a break, I just want to, as you can see there on the screen there, those who want to join the Load Research Chapter via SAIEE, please, you are more than welcome. I'm actually the Secretariat of Load Research Chapter. So that's my email address there. You can contact me. Ismail, thank you very much. Already we have received some colleagues who want to interact with you. So possibly that will happen also via email. We will have a short break. Colleagues, let us be back exactly, because now it's 2 minutes to 11. We're supposed to be back at 11. I will just steal 2 minutes of the other presenter. Let's be back exactly at 11:04. 11:04, we'll be back. Let us take a break. Thank you.
Marcus Lloyd.
Yes, Marcus.
Lloyd, I think we read your role.
All right.
Okay.
Welcome back, colleagues. Our next presentation will be done by Karin Kritzinger. Karin will be presenting to us on the topic of estimated penetration of renewables in South Africa. Karin, she's a senior researcher at Stellenbosch University, and she's also working on another project there. She's the lead for the Southern African Solar Thermal Training and Demonstration Initiative, funded by the Austrian Development Agency. So Karin, because we are sort of behind time with a few minutes, I will just hand over to you. If you are ready, please continue with your presentation.
Hi, everybody. Yes, I'm Karin Kritzinger. I'm a senior researcher at Stellenbosch University at the Center for Renewable and Sustainable Energy Studies. I'm going to give you quite an overview today of basically just all the work that we've done at Stellenbosch University on renewable energy integration into the grid and the impacts thereof, kind of to give you an idea of how the research interests developed. So yes, the Centre for Renewable and Sustainable Energy Studies is a centre at Stellenbosch University. We are funded by the Department of Science and Innovation, and we also host the Eskom Power Plant Engineering Institute, a specialization centre in renewable energy, obviously funded by Eskom. So we fall under the Faculty of Engineering, and we work very closely with SAIEE Solar. We've got the SAIEE Solar Chair in photovoltaics at Electrical Engineering. We've got the Power System Research Group at Electrical Engineering. We've got the Faure Innovation Platform for the Water Energy Food Nexus, which I run, and we've got Arua, etc. So the Power System Research Group is oh, you switched my video off. I was probably looking terrible. So we at the Power System Research Group, mostly with electrical engineering, but there are other departments as well. These are the kind of studies that they look at. So obviously you can see I can't go into every single study. So I'm rather going to give you an overview and give you an idea where you can get all of this information. So the links are at the bottom, and I think the PDF of the presentations will be shared. So I'm going to focus on 4 different studies that we've done, and I'm going to unpack the last 2 in a bit more detail. So the first study that we did was back in 2012, 2013, which was funded by Green Cape at the time, where we looked at the potential impact for a rooftop solar photovoltaics in Hessequa, which is basically Riversdal and some coastal towns there. And just looked at what the financial impact and what the technical impact is. We based our limits on the NRS limits. So, you know, it was all suppose that if people are going to be very, you know, in line with regulations and, you know, wouldn't go over limits, and that it would all be quite nicely done. And the sort of the main outcomes there was, if you keep within the NRS limits, then the income impact and the technical impact is not really that much, and you know, the municipalities would be able to handle that. We did a similar study in 2015 looking at Drakenstein. There we also pointed out that if you stay within the NRS 097 limits, that a 2-hour load shedding event, it actually has a much bigger impact than what so you can see there, it's got a much bigger impact than what the solar impact is, the loss of kilowatt hours from the solar. We just made a little study there that you can just, you know, sort of analysis of, you know, how are the municipalities going to position themselves within this renewable energy? Are they going to embrace it, disallow it, etc.? That was 5 years ago. Things have changed quite a bit in the meantime. So this is the study that I'm going to unpack in more detail. It's a study that was funded by Eskom RT&D. It was a collaborative research between City of Cape Town, Eskom Distribution, the Western Cape, Stellenbosch University, University of Cape Town, and Cape Peninsula University of Technology. There were 3 parts of the study. The study ran for about just longer than 3 years. And it was to look at what is the PV uptake, what is the network integration, what are the problems that one will encounter, and then what are the emerging technologies that you can use to solve this. So basically what the study was is, you know, if we have a rooftop PV, are we going to run it of wires, or are we going to run it of roof space? I mean, at that time, I absolutely thought we're going to run out of roof space before we run out of wires, and it's not really a problem. But boy, was I wrong. I was very wrong. Anyway, so what we did is we started off with a multi-criteria decision-making process. We looked at what is the solar resource, what is the solar resource in different areas in Cape Town, what is the land use, you know, households, commercial, industrial, etc. Looked at what the living standards measure, the LSMs per area, looked at the value and the value of the land and the value per square meter, and then correlated all of these to where the PV was actually already installed. It turned out that the solar resource played absolutely no role. There wasn't, it wasn't different per area. And the LSM data wasn't very useful either. We couldn't find a correlation to PV installations. However, the value of the land per square meter gave a very good correlation to say where PV will be installed. We then did analysis of 3 specific areas. The first area that we did was Landadno. It's a coastal part of the city of Cape Town. It's a nice area to study because it has very definite boundaries. Everybody understands what is inside of Landadno and what is not inside. We looked at all the specific rooftops and divided them between what face they would have, whether it will be east facing, north facing, whether it's a flat roof, etc. And then we did an analysis on what the solar generation capacity would be there, and of course, from the size of the roof, how big a system can you put on there. So these are the results that we got from there, and you can see the peak demand was 1.3 MVA, but our installable rooftop space over there is 6.7 megawatt peak. So you can see you're going to run into problems very quickly there. I mean, it's quite obvious. Never mind that the NRS capacity is 0.2 megawatt peak for that area. So and what actually comes out here as well is, when we speak about renewable energy, wind and solar, we talk about intermittency, we talk about the VRE, variable renewable energies, but actually the problem with installations like these rooftop installations is not really on the variability. I mean, the variability is also a problem, but it's more that it's not that variable. Customer demand is quite variable, and you have it sort of aggregates out when you put a lot of loads together. But when the sun shines on you, the sun shines on your neighbor, and it shines within that whole sub area, and it's not diversified. It will actually generate electricity everywhere. So there's no after diversity maximum demand for sun. It's all just total maximum. Yeah, I mean, you can, the obvious solution for this is just to curtail the generator's output, or just do not have it, just have a meter or a device installed that just makes you not feed into the grid at all. Yeah, the inverters are, and these technical solutions are quite common and quite easy. You can see this was for Century City. So Century City is an office block, and you can see this was much better, even though it was still much more than the NRS maximum capacity. The roof space was actually, the maximum PV capacity of the roof space was actually lower than the peak demand. We also did for Montague Gardens, but there it was also not that good. So the second part of the study was to look at the network integration, the voltages, currents, and the passive feeder. Some of our previous speakers have also spoke to it, what kind of problems you can run into. And I mean, also here, we were trying to get to, something like the NRS 097, which says 15%, 25%, 75%, which has got exact tick box limits, but it wasn't. We couldn't really get to that. The answer mostly was that it depends. In the third part, we just looked at what are the solutions. There are quite a lot of solutions that are quite commercially available. You can do it on the distribution system operator side, whatever Eskom distributor or the municipal side, or you can of course do it on the consumer side, which will be cheaper for the system probably, but more expensive for the actual installer. So these are just the ones that we came up with that are interesting, commercially available, and not that expensive. The second study that I just want to unpack is a study that is funded by Nedbank Green Trust and through the WWF South Africa. It's an ongoing study. We started off with having a survey for households where it was online. It was done in 2018. We had over 2,600 respondents, of which 242 already had PV installed. This was quite a nice sample size because we could compare what people say who already have it installed and people who saying they're going to have it installed, to see what are the trigger factors that actually get people to install. So We asked people about environmental, social, and financial issues. You know, the environmental issues we saw didn't play any role. It's not to say that people are not interested in the environmental concerns. It's just that there's no difference between people who already have it installed and people who actually did it, you know, in their environmental concerns. But social is concerned, we saw that people are highly influenced by people they know. They're much more likely to have installed PV if they know somebody, if they work with somebody. If one of their neighbors has PV, which also means that these installations will happen in specific clusters. And for the financial, it was quite clear that that the high upfront cost is a deterrent for a lot of people, whereas the long-term saving and the business case for the systems is less of a incentive than what the high upfront cost for the is a deterrent. And then, of course, the one thing that really convinced people to install is load shedding, even though we know that PV won't do anything in load shedding. It's the battery, but anyway, let's call it a solar battery. And the biggest problem that we did foresee, which Ismail also spoke about, is that 75% of people with PV indicated that the distributor of electricity doesn't know about the installation. So it seems like the city of Cape Town, with a whole year of a large marketing campaign, managed to get that up to about 50%, which is great, but it's still 50% of people that you need to go after in, I don't know which way, you know. And it's also interesting to me that Ismail was saying that they will go after the industrial and commercial customers first, but the 1,900 households, yes, I mean, that would be quite a nightmare to tick off one by one. It's a bit of a logistical nightmare. So yes, I mean, here I'm just showing, you know, how people, that's, you know, the Eskom, the distributor, and the households, and this is how, you know, all do it very nicely dispersed, but this is actually how it happens, and that's where you get technical problems and you go over limits. And just the perception of how people see, you know, this is a household consumption of about 10,000 kilowatt hours a year, so quite an average kind of household consumption. So if you put a 1, 2, 3, or 4 kilowatt peak system on that roof, it's you know, 100% covered. So yes, you have 100% self-consumption, except if you divide that in months, you see it's that 1 month in December with a 4 kilowatt peak system, you go over. If you put it in hours, then you see, oh my goodness, yes, actually the household consumption is actually much lower than you anticipated. And if you actually look at the 1 minute data, you see that household consumption is actually not something that really happens. This is also confirmed by the City of Cape Town data, where you can also see that the maximum feed in over here is also much higher than the maximum demands over the specific time period. And yeah, you can see that for a 4 kilowatt peak system on this specific individual's house, it seems like it's 100% self-consumption, but actually with the 1 minute data, it's only 44%. The other thing also is with the communication between people. So you can see here, this is what Ismail spoke about, you know, our customers cost us, so we're going to force them to register, etc. But at the same time, you have the conversation with Eskom saying, we actually want to install ourselves, you know, and this is actually this transaction that you have over here between the municipality and the customers is actually the same transaction that you have between Eskom and the City of Cape Town. Somebody needs to pay for all of that. Yes, why, who, why, where, when, why, and how much? Yeah, I think mostly, you know, shopping centers, hospitals, those people who have loads over December, over Christmas, daytime loads, very much, you know, high self-consumption, a good financial incentive. Households will do it. Households, just because they can, it's often doesn't even make that much financial sense. where, all over South Africa, it's not really correlated to where the resource is higher. It's much more to do with where the installers are available, where it's easy, where other people do it. So it does happen in clusters, which does give problems onto the grid, with the neighborhood effect. Why? Yes, I mean,
apologies.
Okay, I've got one slide left. So yes, a lot of people will say they're doing it for environmental. I mean, that is actually the bigger idea. Is actually the only reason we put up any renewable energy is so that we can be more, have less carbon emissions, etc. But in the end, it mostly is this financial decision. Even if you look at international companies that are, according, for trade, they need to have less carbon emissions, and also because of carbon tax, it all comes down on the financial and the incentives. How much is going to be installed? Yes, I mean, it's already, it gives a very good business case for most situations. It just depends on how much what your kilowatt hour charge is, because it's the kilowatt hours that you're going to save and not. And then, of course, you are limited by your rooftop area. And thank you. That's my presentation.
Thank you, Karin, for the allowing yourself to make time and present at our seminar. Unfortunately, we will not be able to take any questions, but please, colleagues, if you have any question, please just post it on our chat group there. Thank you, Karin, for your time. Our next presentation will be done by Aradhna Pandarum. Aradhna, she's holding an MSc in engineering, and she's working at Eskom Research, Testing and Development in Eskom. So she's managing some of the projects in renewables. Aradhna, let me also not take much of your time. Let me hand over to you. When you're ready, you can go ahead and present.
Okay, good morning, everyone. Can you see my screen?
Yes, I can confirm that I can see your screen and I can also see your video. Continue.
Okay, good morning, everyone. My name is Aradhna Pandarum, and I am from Research, Testing and Development in Eskom. And I'm going to be presenting on the statistics of solar PV distributed generation in South Africa. This was based on work that was done in 2017, 2018 for the statistics of penetration of rooftop PV penetration in South Africa. Okay, so as you're all aware, there has been an increasing trend in small-scale solar PV globally over the past few years. And according to Solar Power Europe, the global PV market actually increased by 50% just in 2016. And it's no doubt that there's a business case and other added benefits to these installations. And this is starting to outweigh having to rely on the grid for electricity, and end users are certainly beginning to realize this. So in this presentation, I will take you through some of the data that was collected for the small-scale PV penetration in South Africa. And just note that these installations, which are referred to in this presentation, have a capacity of less than 5 megawatts and are generally referred to as rooftop PV installations. Okay, so this slide shows the install capacity of rooftop PV with respect to total install capacities in certain parts of the world. It's interesting to note that Germany had about 40 gigawatts of rooftop PV, resulting in about 21% of their install capacity. And India just has about 1.5 gigawatts. However, they have a national target to actually install about 40 gigawatts by 2022 of rooftop PV, which will actually equate to about 10% of their total install capacity. So in South Africa, the rules for registration of small-scale embedded generation had just recently been accepted and published by the Department of Energy. This followed the Gazette of Schedule 2 to the Electricity Act, whereby customers are allowed to actually install below 1 megawatt installations without having a license, but having to register the installations. Many customers are actually not aware of this process and these procedures that are and requirements, and this, coupled along with the delay in registering these installations, brings about uncertainty about the penetration in South Africa. And utilities and distributors are actually beginning to experience decline in energy sold, and the uptake of such technology could very well be the predominant reason for this. These installations do not only have an economic impact to our business, but technical impacts as well, as you have seen with the previous presentations. Networks experience voltage rise issues, power quality issues, protection issues, reverse power flow, just to name a few. This all proves that there's a desperate need to investigate and obtain the current penetration in South Africa and know about these things. So this brought about a project in RT&D, and I then collected data from various places. So the first place was actually PQRS. This is a company that is based in Western Cape. We procured the data for installations of rooftop PV nationally with the assistance of GIZ in September 2017. And then I collected data from municipalities that had registration processes in place at the time. And this, as I mentioned, it was between 2017 and 2018. I collected data from about 16 municipalities nationally. And then I incorporated the data from the Eskom Grid Access Unit in terms of the installations that we had registered ourselves. So the overall statistics showed that the PQRS data set had about 212 megawatt peak. The municipality data set had about 50 megawatt peak, and the Eskom data set had about 40 megawatt peak. After removing duplications to the best ability, to the best that I could, I saw that there was about 285 megawatt peak of rooftop PV installed as at December 2017. And out of this was actually about 14.35 megawatt peak of off-grid installations. And this gave us about almost 140,000 installations nationally. This slide shows the yearly analysis of the installed capacity from 2003. And it's evident to see that in the past 5 to 6 years, we have seen a rapid increase of these installations, which is in line with decreasing sales volumes in electricity, rapid tariff increases, and load shedding. So this slide shows the capacity per sector per province. It can be noted that the highest penetration is in Gauteng and Western Cape, predominantly owning the market share to the commercial and industrial sector. This is mainly due to the fact that these provinces contribute to the greater part of the economic activity in South Africa, as most businesses are based in these provinces. Commercial customers tend to migrate to the use of solar PV because of their demand profile following the solar profile, and this results in the most value for money. Included in these installations and the dataset was national installations from companies like GrowthPoint, Unilever, and also residential electrification programs that were initiated by government to electrify rural areas. The major installations from the database was actually Mall of Africa, which had about 4.78 megawatts, Carnival Mall about 4.2 megawatts, and Telkom SA in Gauteng about 3 megawatts. Some other known interesting installations were Clearwater Mall, Standards and Toyota, Two Oceans Aquarium, Kruger National Park, Midas in Bella Bella, and Netcare Hospitals nationally. The overall installations per sector showed that the commercial and industrial sector has about 69.8% penetration, the agricultural sector about 22.5% of the installations, and the residential sector about 7.7% of the installations. This slide just shows the total number of installations per sector per province, and the residential number is actually just higher because of the size of installations being lower than the commercial and industrial sector. In terms of the subsector analysis that was shown from the database, this is the results, and the installations that are for malls actually dominate the market, followed by installations for offices and then irrigation. So in terms of the municipalities, at the time there was about 34 municipalities that had a registration process in place for these installations, and these are the names thereof. In terms of the data that was collected, so the highest penetration actually came from City of Cape Town at the time, which was about 13 MVA, followed by Ekurhuleni with about 12 MVA. And some of the installations known in the database was Empress Palace, Denon, Alberton Mall, Netcare Clinton Hospital, etc. So it's actually interesting to note that the Munichs are also running their own PV programs for their own government buildings. So they have installed installations at their own buildings. And City of Cape Town had a program to install about 257 kilowatt peak for their government buildings. eThekwini had a program for about 294 kilowatt peak, and Ekurhuleni had a program to install about 300 kilowatt peak. The major program that I'd seen at the time was Nelson Mandela Bay had a program to install about 250 megawatts over 5 years in the area. And this program was actually supposed to start this year. So in terms of the financial business case, some of the municipalities also have approved net metering tariffs to make it more attractive to their customers to install. So this was financial year 2018, and the highest tariff at the time was Nelson Mandela Bay, which was actually offsetting their tariff of their customer, which actually maximized the benefit to the customer. So in terms of the data, I actually tried to maximize the benefit from the data sets, and I saw the following. The most common and average sizes for the sectors and the most common sizes for the different sectors was actually available in the data set. And as you can see, for the residential sector, the most common size were about 3 kilowatt peak. For the agricultural sector, the most common size was about 50 kilowatt peak, and the commercial and industrial sector was 10 kilowatt peak. I also looked at the number of installations for the different sizes of installation, and most of the database was actually made of installations from 0 to 50 kilowatt peak. So why is this uptake of this technology so rapid? Karin had given some reasons as to why, what she had seen, and globally what we've seen on our side. So in terms of who is most likely to install in the residential sector, it was actually high-income homeowners that had freestanding homes. In the agricultural sector, it was customers with non-seasonal electricity consumption and that had availability of funding. And then in the commercial sector, it was the building owners, such as your shopping centers, your grocery stores, offices, and distribution centers. Also coming into play in terms of the factors that affect uptake is your payback periods. So residential sector had seen that they would accept a payback period of 5 years. But for agricultural sector, they accepted a payback period for less than about 6 years for system sizes that had under 50 kilowatt peak, and then less than 10 years for the larger systems. And then in your commercial and industrial sector, it's generally between 0 to 10 years, but ideally between 0 to 5 years. So in terms of the financial business case, I actually looked at some of the levelized costs for the PV systems in terms of your residential sectors and your commercial systems. Looking at the installation costs and the decreasing costs thereof, this actually shows justification as to why customers are migrating. If you're looking at your rands per kilowatt hour and your current tariff, it's basically matching already in between 2018 and 2019 for the different sectors based on what tariff you're on and where you are. The municipality tariffs are a little bit higher than the Eskom customers, so they might actually see a longer period, but regulation also comes into play. So some customers are uncertain about regulation and not sure whether they should install and why and how they should actually do it. So everything actually needs to be taken into consideration. So in terms of the growth prediction for the PV penetration in South Africa, we've actually looked at different scenarios, and these scenarios were based on projections that we've seen from a French institute that was previously published for South Africa, SAPVIA estimates, the IRP assumptions, projection of actual growth to date from the data that was collected, and as well as incremental growth rates of 5 to 10%. I personally think the high growth scenario is what we are actually going to be experiencing due to the current electricity situation in South Africa. And at this moment, it actually estimates current PV penetration to be about 600 megawatts with installed capacities of below 5 megawatts. But other factors could not be directly accounted for in these growth predictions that directly affect the growth. That is load shedding, the increase in available funding, like Nedbank had been offering loans and advising their customers to install these green energy installations. Political impacts, the increase in tariffs that we've seen, the MYPD applications that Eskom had been applying for, regulation changes and implementation. So you could also start seeing something to the likes of import taxes that could be implemented for our PV modules, or stringent rules could be enforced if not installing per regulation or as per regulation. And now the installation of something called a dead grid safety law could increase your capital amount that is required for these installations. So these changes could make the installations more expensive as well. But then you also see tax rebates and incentives. So SARS gives you a 28% back tax rebate on your installation cost in your first year if you are registered as a business. Companies can also see 100% depreciation from the first year after purchase for these installations, as well as per SARS laws. And then you also see power purchase agreements. So customers are being offered a rand per kilowatt hour or a rand per kilowatt hour agreement for the next 15 years or 20 years, depending on how long you want the installation for. So you don't have to put the capital amount down yourself. You can just pay per usage as you are paying your utility. And then now the COVID impacts. So what I've already been seeing that there is increasing costs in the inverters and the panels already. You're seeing it because of COVID and you're seeing it because of load shedding. You'd never know which one it is for. So these numbers may be over or under predicted, and the best we can do is actually make an estimation and act accordingly in how we prepare for it and treat these installations. Because like it or not, I think solar PV and embedded generation is here to stay. So yeah, we can just prepare ourselves. Thank you.
Thank you very much, Aradhna. You just finished right on time. I did not have to cut you. Thank you very much for the time, allowing yourself to prepare and also to present at our seminar. We truly appreciate that. In terms of my chairing this session, this is the end of my chairing. I just want to thank and appreciate all the presenters who presented during the session that I was chairing. for the very informative presentations they have made. I'm aware from my side that we actually needed more time. And I think in future, we will discuss as the Executive Committee of Load Research Chapter on how to arrange another platform going forward where we will be able to give more time so that we can discuss these issues in a deeper way. So yes, we have received the overview of policies, regulations, and standards around PV, particularly for network planning. And also we have also seen in terms of the penetration of PV in South Africa. So that information actually is very much important for us to be able to close some of the gaps when you look into the perspective of network planning. So the issues of tariffs, the issues of metering, all those questions that will arise as PV penetrates our networks, we will need to answer those questions. So this seminar also are seeking to answer some of those questions, but as time moves, as we continue, I think those questions will be answered more clearly. Thank you very much from my side. As you can see again there, if you want to join the Load Research Chapter, you are more than welcome to send me an email. That's my email address. Again, my name is Lloyd Setlhogo. Thank you for the time you have spent to listen to me and listen to the presenters. We are now going to have a break. It was supposed to be a break of 15 minutes, but may I request that we take a break of 10 minutes? Can we be back at 11:55? Thank you very much. Thank you.
Hi everyone, it's Marcus Dekenah here. I'm a co-chair of the Load Research Chapter. This session will be about the different approaches to estimating network load impact. What you've seen in the earlier session is the previous presenters setting up for this session. We've had Crescent talking about the underlying load shapes of renewables. We've had Faure and Avinash and Ismail talking about the regulation which controls how the customers behave. Then in the following session, you've had Karin, Kritzinger and Aradhna talking about the potential impact, the potential penetration of renewables on the system. And now we come to the final session, which is, well, the penultimate session, which is about the approaches to estimating the load impact and really how the municipalities and other bodies go about estimating and planning for renewables, giving all of the aforementioned. The very last session today will be from the very last session, presentation in this session will be from Aradhna. We will talk about some issues around voltage regulation in MV systems. So without further ado, I'm going to hand you over now to our first speaker, who's Paul Vermeulen. Paul is a chief engineer for renewable energy at City Power, and Paul has quite a few very innovative ideas about renewables and how to handle them for greater network utilization within a municipal environment, and that municipal environment is City Power. So without further ado, I will hand you over to Paul. Paul, I'm just going to give you the screen now.
Thanks, Marcus. Good afternoon, everyone. And while Marcus is setting up there, thank you for the opportunity to share some information from City Power. It really is a very fast-acting and changing environment, I must admit.
Paul, you have the shot. I have your screen sending, so you're good to go. Thank you.
Thanks, Marcus. Right, ladies and gents, you know, one of the big questions that comes up is in fact why do we need to support renewables? And pretty much, you know, it's a planned thing. It's evident in the RP's 500 megawatt per annum allocation for this type of generation, and that's for the next decade. You know, City Power said, okay, if that 500 megawatts, if we are 10% of the national load, then we're actually looking at 50 megawatts a year for the next decade, which means that by 2030 we probably should have. Let me just switch that off. It's complaining a little bit here. We should have 500 megawatts of photovoltaics at least on City Power's network. The other aspect is that distribution networks are public assets, and they're there to serve the needs of all the users of the grid. And that's something we often seem to forget. There is definitely a need for customers for grid-supported access to cost-effective distributed renewable energy sources. And there's also an emerging complementing need for grid access for appropriately scaled distributed energy storage facilities in order to complement this renewable energy and the intermittency, in particular, of the renewable energy that we're expecting to come on. These needs are driven by several motivating factors, and there's two aspects. There's the financial side, energy economics. The renewable energy is becoming cheaper, in fact, even than Eskom supplied. Certainly, as has been previously mentioned, rooftop PV is definitely cheaper than the municipalities' rates at present. So we see the effects a lot quicker than the Eskom areas. We've got carbon tax and renewable tax incentives in place already. Another clear financial driver. A lot of our bigger commercial customers have taken advantage of those tax incentives. And a lot of businesses are under pressure, in fact, to prove that they are purchasing renewable energy or green energy in their production, in the production of their products. And also, of course, it's the whole climate change issue, and the city has got some seriously big targets in respect of meeting those targets. You know, one of the other things that we often do, and I use this slide at a lot of other seminars and webinars, particularly the AMEU, we often take the grid for granted, and particular society, and perhaps it's our own fault because we don't promote the grid for the value that it brings. You know, diversity, the average person doesn't understand what diversity is, and it's quite important to get that idea across to them. And also the idea that the people that are connected to that grid are part of an interconnected community. You know, that's how we make the financial side of things work. Cross subsidies, supporting industry, all of those things are part of being part of that network. And the minute you destroy that sort of relationship, these systems tend to fall apart. I must admit, I get very irritated if I go to a braai and somebody says we're going off grid. And they're not really sure what the reason behind that is. It's just, they're sick and tired of city power, they're sick and tired of Eskom. What we do need to do is start working with our customers and convincing them of the value of the grid. That's really the purpose of this slide. So our connection process, you've heard very much about this, the Cape Town process, very, very detailed process that is, I must admit, and take my hat off to them. They are pretty well organized by comparison to Joburg, and I've got to acknowledge that. But the process that we have is part of the service connection process. A call is logged on SAP and it's processed via the planning department. Our little renewable energy section examines the application in terms of NRS 097, the simplified connection criteria, the proposed connection schematic, and usually we also ask for an operating philosophy, how the system is going to be operated. And then the most important is the inverter NRS test certificate. In principle, approval is given if all those criteria are met and the use of system agreement is signed. It was mentioned that systems above 100 kVA need to be registered with NERSA. That is subject to this use of system agreement. So the first port of call is in fact us. If we deem it's possible to absorb this onto the network, we then request that customer to sign that system of use of system agreement, and then it's up to them to go and register with NERSA. We did ask NERSA if we could do that on behalf of the customers, but that's not possible. They need to do it themselves. If the proposed system capacity is above the simplified connection criteria limits, then we advise that customer that a comprehensive network study is required. And that's usually done by a private and outside company at the moment. We are trying to build our capacity internal to City Power to provide that as a service, for which there would be a fee charged. And also in the case where the proposed system is greater than 1 MVA and it's been confirmed that the network can accommodate it, we advise that that customer must make an application to NERSA for the generation license. In the process, 4-quadrant metering capability is enabled or installed, and then following the construction, the system is jointly commissioned with a staff member from City Power to confirm that dead grid separation does actually happen and that the equipment installed on site matches that application, and of course that there is a valid CFC. So our uptake statistics, these are the commissioned sites that we've got. The total capacity that we've got as at the end of June, 44.2 MVAs worth. Total number of residential systems is 42, which is really a small number. You'll see in the next slide why I say that. The total number of commercial and industrial systems we have commissioned and registered is 184. The average system size there is 240 kVA, and that's where the most of the commissioned capacity sits, 43.92 megawatts. Our three top sites in terms of system capacity: FNB Fairland 1.925 MVA, Stone Ridge Shopping Centre 2.1 MVA, and Clearwater Mall 2.67. private capacity PV to be normalized. We had an interesting project very recently with the C40s network and the city of Joburg, where the University of Johannesburg was commissioned to do a study of how many solar water heaters were installed in the metro. The study used AI to pass aerial photographs, recognize and count solar water heaters. 129,000 of these were found with a confidence of 88.7%. The system was also programmed to recognize solar PV installations, and a whopping 33,800 of these were found. And I've got to admit, this is with 2016 data as well, so it's already old data that was used. The aerial photos were from a few years back. So this number is probably a lot higher than what we see here. And it is a significant number, possibly an additional 90 MVA minimum, I would think. And a normalization process is required to ensure compliance to accepted grid interface standards. But amazingly, we have not yet been inundated with quality of supply complaints, particularly in those northern areas where you see the blue dots in the picture. That's predominantly where the systems are. This is a sample plot, but it gives a good idea of where the general distribution of these systems are. In terms of quality of supply monitoring, in order to determine if there were QoS issues, the decision was taken that any system greater than 300 kVA, we would install a quality of supply meter. And no significant issues have been found so far. So I think from the point of view of the professionally installed systems are generally compliant. It's perhaps the systems that we're not aware of that might be the issues. So we haven't really had issues of voltage rise on the Crescent Mall, for example, and things there have been within acceptable limits. If we look at NRS 097, the voltage rise limiting effects, it's very true that limiting the size of the system in terms of the service connection size has had an effect of limiting the effects of voltage rise. But also part 1 of NRS, where it describes what standards the inverters must apply to. Certainly for category A1 and A2, there is an overvoltage functionality that requires the inverter to shut down, but it's more of an abnormal condition kind of shutdown. It's not intended as an overvoltage or as a voltage regulation mechanism. But I'm quite sure that this is helping us tremendously in terms of preventing voltage rise on these many systems that must be connected to our networks. For category A3 and above, the systems must regulate voltage as per the renewable energy grid code and be controllable by the distributor. So we've certainly made sure that those systems that are of that size are ready for SCADA signals from our side. We've also gone down this path of trying to find our new energy mix, and recently with strategic partners, we've been doing feasibility studies within these 6 main work streams: solar PV, energy efficiency, energy storage, waste to energy where that may be available, electric vehicles, and also gas. In Joburg, we've got gas pipelines under our feet, so gas generation for peaking plant is very much a possibility for us. So those regional resources are being factored into this, and it's come up with some interesting results so far. Also, you're going to need a different mix of energy on the different intake points. Certain intake points we've already seen NMD penalties. It makes sense to focus a little bit of energy storage on those intake points, for example, but each is different. We've got something like 44 different intake points, and each has a different load profile. The main objective of this new energy mix is also to present Eskom with a much flatter load profile. Part of this is to reduce costs, and certainly from the planning side, at least the capacity at the top substations, you want to try and limit downwards if you possibly can, and things like storage and peak clipping DSM systems are what we really need to make sure go in. So one of the things we're very interested in doing is expanding support for customer PV connections. Now, at the moment, we're very well we're accustomed to the own consumption, own roof model, and this is the most destructive in terms of our revenues. But if we enable wheeling and trading, own consumption does not limit consumers to own roof sources. And what it means is that we now will have a new source of revenue through wheeling and trading energy charges. We did apply to NERSA this year, however, they didn't approve our wheeling tariffs on the grounds that they first want to see the cost of supply study, which has been a bit delayed from our side. We're also very interested in developing our own portfolio of renewable energy. So as a city, we've got ambitious CO2 emission reduction targets to meet. The city has plans to provide carbon neutral municipal services, hopefully by 2030, and that means we need 265 gigawatt hours worth of energy per annum for things like water pumping, water purification plant, to offset street light consumption, and also offset energy consumed in buildings where the council has offices. In terms of the Municipal Systems Act, we are also obliged to provide energy services from the least polluting and lowest cost options available. And we are very interested in creating our own portfolio of renewable energy sites. And we see those taking effect as being city-owned PV sites located on city buildings and open land that may be owned by the city. Joburg has a lot of mining land available that you can't really build on, but you could in fact use for PV, small PV farms. And they're all within 3 kilometers of the NV distribution network. We also see IPPs that may be able to operate on that land for us. And we also see IPPs on private land or buildings within the city limits. And here we're thinking that our 11 kV network is pervasive through the metro. If we go and look for the warehouse type roof partner with them, get an IPP to put PV panels on their roofs, and the energy feeding into our network with City Powers as an off-taker. This is one of the options that we're seriously looking at to see how we can get energy into the grid, renewable energy, of course at an affordable price, and at a price that won't escalate at the same rate that Eskom power is likely to escalate going forward. As I've mentioned, dispatchable gas generation sites are also part of the new mix. So we would overlay the gas pipeline in relation to substations and have a look where those opportunities present themselves. Our old Cottesloe gas turbine site that was run on diesel can also be converted to gas, and a new peaking plant created there. So really the question for us is, how far can you really push things now? So municipal distributed networks, if you look at our networks, they are bottom heavy. So most of the equipment is down at the MV level. You know, if you look at the One Tower Island on the right there, Prospect substation, we've got 762 MVAs worth of firm transformer capacity at 275 to 88. By the time we've sub-distributed that or sub-transmitted that to our 88 11 stations, the transformer capacity sits at 1500 MVA. And by the time we look at the mini subs on the street corner, we've got a whopping 2.5 gigawatts worth of transformer capacity installed. So the capacity is certainly there. It's just how you use that and how you can use it without causing issues is the trick. So far, the NRS 097 has been a useful guide, but I think the existing MV networks, you know, the capacity, the hosting capacity is what we really need to look at. And I do believe that a lot more can be pumped into that network without necessarily causing problems. Immediately, what we have done at City Powers is to upgrade our network modeling software, our Big Silent application, and we are trying to build capacity within our planners to factor in these new technologies and new options into their designs. I do think that we really need to talk a lot about energy storage as being part of this new mix. You know, this at scale applied to a grid, this has tremendous value. Optimizing energy procurement costs through arbitrage, we use it very much similarly to the way you would use an old user control system. You you defer peak energy purchases, protect the economy. A lot of storage on the network could make you reasonably bulletproof towards load shedding. I think encouraging customers to invest in energy storage rather than diesel is a worthwhile thing to do, and to include that in the communication and convincing customers in which way we need to go. Preserving overloaded distribution infrastructure where you've got bottlenecks at distribution level. Energy storage can be put behind the bottleneck and solve that problem. Voltage regulation, we've seen the issue of photovoltaics pumping into the system with a constant load curve. That little fluffy cloudy day, that's a problem. You have this power that comes and goes within 30 seconds. That causes big problems with voltage regulation. Energy storage can solve those problems as well if it's put in the right place on the network. Storage can also support densification, unlock property development, and optimize investment in renewable systems as well. And also there's a role to play with storage for providing basic energy services. It does all depend on where we place them on the distribution network and how they are operated. So already a network study that looks for network hotspots and starts to say these are the places where we need to install the energy storage systems, definitely do need to be part of the distribution planning master plans. So storage is a very powerful grid management tool that network planners can start to include in the design processes. So the recipe for reducing the peaks would be to install storage. If I look at that same Prospect Power Island, and we managed to get 350 megawatts worth of PV generation introduced there, we're probably going to need 250 megawatts worth of energy storage with a capacity of around 1650 megawatt hours to try and smooth that curve so that we can reduce the cost of buying power from Eskom.
Paul?
Electric vehicle charging, it's almost the last
1 minute, please. 1 minute, thanks.
One of the issues here is that the requirements for EV charging are not energy heavy, but they are certainly capacity heavy. You know, if you look at the tables here, you'll see that a fast charging system requires somewhere between 30 and 60 kilowatts. So you go and put a whole bunch of these around your network, you're going to very quickly end up with capacity constraints to support this. The table below sort of took a view of what could we expect the growth in EVs to be, and what would the peak demand be to service the charging. And you can see that by 2035, things get to 7 gigawatts worth, which is a huge number for Joburg alone. But I think the point I wanted to make here is that one of the things that has happened with energy efficiency is that developers have said, you know, we don't need the 5 kVA ADMD capacity that we did in the past. You know, energy efficient lighting and appliances has really dropped things, and a lot of them were saying we only need 2 kVA or less per earth for electrification, and we've resisted this so far because of what we see. The electric vehicle is on its way. We don't want to end up in a situation where the networks that are going in today are too weak to support that. So in conclusion, I think networks planners, the grid is key to making this whole thing work. So the network planners already need to design their networks in an embedded generation ready manner. It means that along with the traditional centralized and top-down model, they do know so well, they must also design bi-directional energy flows in mind. And it also means moving from this mindset of limiting the power received, the conservative approach, to limiting the power received from embedded generation, to rather a position of optimizing the evacuation of power from them. And the future that includes a combination of intermittent resources and large transient loads will also require a leap of faith. What I have found of planners in the past is that they'd rather over-design the network so that it can take whatever is thrown at it. But you're moving into a mode where you've got to start relying on the smart grid and control functionality as also part of your network planning process. And that's from the City Power point of view. Thank you.
Paul, thanks very much for your presentation. It is much appreciated. I will now share for the next presenter. I think we're out of time for questions. If those online can just confirm that you can see a slide for Mpeli Ramponkanyo. Okay. Our next speaker is Mpeli Ramponkanyo. Mpeli is a principal engineer at CSIR, and he is currently providing research leadership in an area of power system operations for the current grid and future energy system with high share of renewables. Now, one of the first places to start with planning is where you have a smallish system and you can really understand the possibilities of fairly good planning control. And that is the microgrid situation. So Mpeli is going to speak to us about that, and without further ado, I'll hand over to Mpeli.
Hi, Marcus. Thanks a lot for that introduction. I don't know if I'm audible.
Mpeli, you're audible. I'm just going to make you a presenter. You should have presentation now.
Yes, I do.
Your audio is good. Please carry on.
All right, thanks a lot. Right, afternoon, ladies and gentlemen. As Marcus has introduced me, my name is Mpeli Ramponkanyo, and I work at CSIR Energy Center. I'll be taking you through a microgrid project that we undertook at Upper Blinkwater in the Eastern Cape, and we are still undertaking this particular project with a number of stakeholders. So without further ado, I will carry on with the presentation. This is just a brief outline of what I'll be discussing with you. The background to the project, study objectives, assumptions, some results and analysis, specifically load flow results that we did in dispatch optimization studies. I'll also take you through a dispatch strategy algorithm that we designed for that particular microgrid, and then conclude. So in terms of the brief background, the microgrid pilot project was initiated for the electrification of the remote village of Upper Blinkwater in the province of the Eastern Cape in South Africa, which is 23 kilometers northwest of Fort Beaufort, which falls under the Raymond Mhlaba local municipality. So this is the project that we undertook, like I said, with multiple stakeholders. The designed microgrid for the village is a hybrid system, which includes a photovoltaic system, a wind generator, a battery bank storage, and a diesel generator. We, as the CSIR Energy Center, were appointed to spearhead the wind component of the project, and we looked at resource assessment, overall system integration, grid modeling, and knowledge transfer, particularly to one of the stakeholders that we're dealing with is a Faure University. Those are the people that will be transferring knowledge to. In terms of the scope of the study, the objective was to conduct a load flow study that assesses the impact of integrating wind generation to Upper Blink microgrid. Just hang on, I would like to pop out something here. Something is not working on my side here. But anyway, so this is the objective. It was to conduct the load flow study, and looking at the integration of the wind specifically. Then the crit or the microcrit is made up of the photovoltaic system. It's made up of a lithium-ion battery bank and a 55 kVA backup diesel generator. The other objective was to conduct an optimization study that identifies the best possible dispatch pattern to minimize the occurrence of load shedding and excess energy on the UB, that is the upper blink microgrid. And the load flow study was done on Dix Island, while the optimization studies were done on the home modeling environment. This is just a geographic schematic of the microgrid. As you can see, it's a long feeder right in the rural of the Eastern Cape. I think one thing to mention is that there is no Eskom electrification at this point in time, so the village was unelectrified. One of the big issues that we had to deal with for an unelectrified system, or rather village, as I've explained, was to do load modeling for the village. It became cumbersome and a very difficult process, as we had to we didn't have data for any typical rural village that could represent upper blink battery. So what we did, we got some data from Eskom of the Greater Bisho area, which the Raymond Municipality, we believe, falls under. And we modeled that and sort of like scale it down to reflect the upper blink battery peak. So we did just a scaling down of that. So that is a bit crude, yeah, because the real thing basically would be to have done a typical village profile, rather than using the greater municipality, which could institute industrial load, which a normal residential would include. So we looked at a number of scenarios for the load flow. One of them being the winter case scenario, where you're looking at high demand versus low generation. I think it has been said by a number of presenters, and especially the keynote, that we are using deterministic methods, for undertaking, power system and this sort of like modeling studies. Those are traditional methods, so they sort of like fall short. So, but they are still important for load flow studies when you are looking at things like voltage. Profile of the actual network. So we undertook such a scenario where we are comparing the PV generation and wind generation with the demand or on the grid. And as it can be seen on the first scenario already, we had a generation deficit, simply because load flow would be looking at a snapshot in time. And if we have to compare it with the generation snapshot at a particular time, in terms of the production that we used some program that we took from the internet called Renewables Ninja program to generate generation profiles. So you will see that you come up with deficit because the renewable generation basically is variable and is not dispatchable. So you can't really necessarily follow the load like you'd know under a normal traditional situation. Further on, we tested the other extreme scenario, which was like a summer minimum type of thing, which you normally do, to check your voltage, profile. I'll not be showing the voltage profile per se, but I just want to make a point that, there is that mismatch of generation and demand because of this variability. So if you look at the time of 11 o'clock or so, that we took, we had a surplus generation, you would expect, because PV peaks during the day. So you had a bit of surplus generation, which obviously you would want to store somehow if you have a battery storage system. Otherwise, we'd have to discard and dump that energy, which becomes the which becomes wasteful. So those are some of the load flow scenarios that we studied. And like I have said, the limitation of load flow is that because again, it was not a temporal load flow, Dix Island offers that functionality, but we're mainly concentrating on just checking the stability of the Kritzinger as far as voltage is concerned. So it was not temporal. So the limitation there was that there is this big mismatch in load and generation. And this calls for generator dispatch optimization studies that we also undertook, that I'll be presenting to you in a brief second. Then the other constraint, obviously, like I said, is that renewable generation is not dispatchable. And then you need to have flexibility in terms of battery storage or maybe even diesel to actually supplement or complement that generation. So just to take you briefly on the optimization studies that we did under the HOMA environment, we had to look at dispatch strategies that were inbuilt in HOMA. This constituted 4 dispatch strategies already that were inbuilt in the program, or rather in the software. That was cycle charging, that looks at the generator, that is the generator operates at full capacity and excess power from the generator. Is used to charge the battery. Then the other one was load following strategy. And the other one that we looked at is a combined dispatch strategy. And then the last one was predictive dispatch strategy, which basically looks at a foresight of 48 hours, and it aims to maximize self-consumption of excess energy so that the energy curtailment can be minimized. So now just to compare the dispatch strategies that we undertook under the HOMA environment, basically being employed on the crit, the microcrit that is under study. We first start with a cycle charging dispatch strategy, which had or showed an LCOE, which is levelized cost of electricity or energy, of about R2.73. With an operating cost of over 600,000. And we can see that there was a bit of load shedding there and an excess electricity production of about 14,000 kilowatt hours per year. If you compare that with another strategy that we employed, which is the combined dispatch strategy, it had an LCOE of 356 rands, sorry. With operating costs of 878,000, sorry, and an excess production of 77,000 kilowatt hours per year, which is obviously poorly performing compared to the previous variant. The last one that we looked at was the predictive dispatch strategy, and then this one had an LCOE of R2.59. With an operating cost of over 600,000, and excess electricity production of 6,000 or so kilowatt hours per year. Already you can see that this becomes a bit superior over the other 2 strategies that I've discussed. The predictive strategy, because it has this foresight. So the key takeaway from the dispatch strategy is that although predictive dispatch strategy appears to perform better than the other dispatch strategies, there is still a lot of energy produced. There's still a lot of excess energy produced that could easily be dumped if the battery storage is not available. And so we further on looked at optimizing the sizing of the battery and for production or for optimal production using predictive dispatch strategy. As we've seen that it became superior in our analysis. And then this is just the comparison of those dispatch strategies that we undertook. So if you look at the table, you'll see that for the predictive dispatch strategy with 2 batteries that is on the ground as we speak. I have shown that there was an excess energy of 6,362 kilowatt hours per annum, with a corresponding to around 59 cents LCOE. If you increase the number of batteries using that same strategy, you go to row 5, that is highlighted in green. Then you see that automatically the excess energy is reduced to 325 kilowatt hours per year, and the system LCOE is 274, which is slightly greater, but you get the benefit of saving on the excess energy that you could easily dump, if your battery is fully charged. Then you go further to integrate even further, maybe in terms of more batteries, 6 batteries. You see that yes, it does reduce your excess energy, but unfortunately it increases the LCOE to 298, and then further on 8 batteries under the PS strategy, which is the last row, decreases the excess energy to 51 kilowatt hours per annum, but because of the additional cost of extra battery, the LCOE is increased as well. So safely to say that the 4 battery case under PS, or rather predictive strategy, was superior, and that's the one that we recommended for implementation onto the grid. So just to take you through the logic design that we undertook for the predictive strategy, because it's inbuilt in HOMA, but unfortunately HOMA, I think because of proprietary issues, they don't necessarily share the logic. We had to dig in a bit to find out exactly what's behind the actual predictive strategy. Yes.
Apologies, 5 minutes. We came in with a bit of a penalty for you, but 5 minutes should give you full time. Thanks.
Thanks a lot. Yeah, almost there. All right. Okay. So in terms of the logic design, we had to design the predictive strategy algorithm, and these are just the inputs that we put into the design. There was a reserve margin that we had to define, which basically, for a predictive strategy, if you remember, I said that it has a foresight of 48 hours, and it maximizes self-consumption by reducing, excess energy. So basically, what happens is that it looks into the future, and if there is forecasting in the future, if there will be excess energy, then it makes a decision today to discharge the battery, simply based on that foresight that tomorrow I will be having excess energy to charge my battery. So then we had to be careful there that we don't become ruthless or reckless in as far as that is concerned. We define some kind of margin, some safe margin, that we could say this thing could safely, discharge the battery once that margin has been achieved. The margin in terms of between generation and load in the future. So we define that margin to be about 30%. So that's the reserve margin I'm talking about. The other input cost that we put, or the other inputs that we put into the strategy, were the cost of discharging the battery. Yeah, so that's given by that formula that I will not go through, but it's a very straightforward formula. And the other input was the cost of running or turning on the diesel generator as well. It's defined by that formula that you see on the slide. It's pretty much simple as well. It's not difficult at all if you follow what the slide is saying. It makes perfect sense. And so in terms of the strategy itself, the predictive strategy, we had to define it as given by this slide. It will start first with recalling the load demand that you have, the current load demand that you have, and compare that with the total RE generation that you have. So if we have surplus, which is given by that first branch, if you have surplus where PV plus wind is greater than your load, then you have to make a decision whether you want to charge or discharge the battery. So that's the branch that goes towards the left onto your screen. And otherwise, if you have a deficit, which will be the no logic, right at the top, then that means that you are having a deficit, and then you have to make a decision whether you want to run the diesel generator or you want to run there or discharge the battery. So that's where that those costs that I showed you come into play in terms of which one is better to use. So in a nutshell, that's what this logic diagram does. And I think it's sufficient explained. If you go through it nicely, I won't go through the whole of it. It does make perfect sense. So in terms of conclusions, the simulations have shown that the optimal dispatch strategy for wind integration at UB or upper blink battery would be the HOMA predictive dispatch strategy, because it stays fuel over the entire life of the system. And on the other hand, the combined dispatch strategy and combined charging, or rather the cycle charging strategies have shown not to be optimal. The optimal battery bank capacity was found to be about 4 by 65 kilowatt hours, which I've already shared with you. And this helps reduce the excess energy that was seen rather in the base case of 2 batteries. And this unfortunately has an added cost of, or additional capital cost of about 920, which is close to $1 million, but it still has an LCOE of R2.74. So those are the conclusions. And further on, we are anticipating that there will be increase in demand in the microgrid. But we think that this future increase in load will work out positively, as it will help to reduce the excess energy seen currently. So that's about it. Thanks a lot, Marcus.
Thank you very much. Excuse me.
I hope I didn't go.
Thank you. Yeah, thank you very much for
the time.
No, that's perfect. Thank you very much for your presentation. I think you've demonstrated the value of optimization, and I must congratulate you on giving one of the most complex goodbye slides I've almost ever seen. That program flow, very impressive. Thank you so much. I want to make that a wallpaper on my computer for a while. I thank you, and we'll move on to Sipho Mbuli now. Okay, our next presenter is Dr. Sipho Mbuli. Sipho is a chief engineer. Sorry, the slide is incorrect. I will speak the right words to the wrong text. Sipho is a principal researcher at CSIR, and one of the things that Sipho does not say in his bio is that he was part of the project team on one or more of the South African IR integrated resource plans. Sipho is currently employed by CSIR as a principal researcher and is a member of SACNASP. Sipho, you can perhaps explain what it is when you're given the screen. I will now make you presenter.
Okay.
Coming up. Okay. Sipho, you have control now. Your picture is good. It's building.
Okay. Thank you, Marcus. Good afternoon, everybody. Am I on the
presentation
mode already?
Okay, all yours.
Yeah, thanks everybody. Good afternoon, everybody. Thanks for tuning in and taking the time to listen to my presentation entitled Integrated Renewables Planning for a Commercial Campus. The layout of my presentation is as follows. I'll very briefly talk about CSR as a company, and then talk about the study objectives that we needed met in this campus RP. When we were doing this CSR campus RP, we considered a total of close to 20 scenarios. I mean, for purposes of this session, it is not possible. So we're basically going to sample some of the study cases. Then I'll talk you through some of the input assumptions that went into the model, as well as the methodology that was utilized in order to produce the least cost plan. Very briefly talk to you about the research-based plan. The research-based plan, how it was built on top of the least cost plan. And then also we'll look at grid resilience, where we look at the adequacy of the least cost plans to meet demand in the event of grid outages. And then the last slide will be some recommendations. CSR has an annual electricity demand energy of 30 gigawatt hours. It has a base load demand profile of 3 megawatts with a peak load that ranges between 5 and 6 megawatts. I'm not going to just bore you with all these other details. You can just Google this. As of today, CSR has installed a total of 2 megawatts of solar PV on site at different times, all of which have a levelized cost of electricity, which is significantly well below the cost of SAIEE tariff. The first solar PV was actually commissioned in 2015, 558 kilowatts, followed by the dual axis tracking in 2016, which is the highest levelized cost of electricity at 104 cents, still below the SAIEE tariff. But the business case for this option was significantly less than the SAIEE tariff. In terms of the typical demand profile at CSR, the slide shows the summer and winter demand profile, and you can clearly see that 3 megawatts of baseload demand profile. Of course, the situation right now is very different due to COVID-19, but business operation will return. Normal business operation will return at some point in the future. So the study was done prior to COVID-19. So yeah, this actually formed the basis of our investigation into the integrated renewables planning for CSR. In terms of the some of the sorry, what happened here? My bad. I think the slide jumped quite a lot. In terms of the critical questions that we want answered, the idea is follows, right? What are the least cost pathways that are accessible to CSR? What price can CSR expect to pay in the future for electricity? What portfolio of electrical energy supply option will minimize CSR's electricity cost? When should CSR invest in new supply option? How much of the load can CSR supply if the grid is on outage? And what is the impact of changing the current municipal tariff on the least cost plan that we produce? All right. In terms of the sample of the study cases that we considered, I'm just showing a few here. This presentation will just focus on the red circles here, but the business as usual, also abbreviated as BOW, is the starting point. It actually represents, we'll give detailed exposition, it actually represents the status quo that is perpetuated into the future. We change nothing, we continue with the system as we had it as of 2019. Now in the least cost plan, we include new supply options, solar PV, biogas, wind, battery, thermal storage to minimize costs. That's on the supply side. On the demand side management options, we look at replacing some of the older solar water geysers, older inefficient HVACs, as well as the fluorescent lightings with efficient lighting. Now the tariff sensitivity is when we play around with the Eskom's megaflex tariff structure, and we test the robustness of the least cost plan, given that now we're changing the tariff. And we'll talk about the basis for changing the tariff. Some of you may already guess. The research-based plan is built on donor-funded options which we believe will be donated to CSR who acquired at a significant discount. We talk about 3 megawatts of battery options, as well as the 2 kilowatts of small wind turbine. Right. Grid resilience, we quantify the extent to which the CSR list cost plan is able to meet demand in the event of a grid outage. So this is now detailed exposition of the business as usual. The business as usual, this is the energy, CSR's energy demand, annual numbers, that's the makeup of those annual energies. In the business as usual, what we assume is that this status quo is perpetuated into the future. So that becomes now our reference line, our zero line, right? In terms of cost, in terms of emission, in terms of water consumption, right? So everything else that we do will be compared to this particular scenario. So in the business as usual, currently I've showed you that CSR has approximately 2 megawatts of solar PV. So the 2 megawatts together with Soni will now be used to meet this business as usual demand profile. Right. Soni option comes with the tariff. This is the structure of the tariff composition. 77% is actually sitting on the energy charges, and the complement is sitting on the peak charges and the fixed charges. All right, peak demand charges as well as the fixed accounting charges. So the graph in the middle shows a typical summer and winter tariff. All right, so this is based on the Eskom's it's based on the Eskom's electricity demand profile. You can see it here. This is the proper kind of the tariff kind of mimics the Eskom demand profile. So we have not really reached a stage where existing installed utility scale PV, including the distributed PV, is actually producing so much that we start experiencing what's called the dark curve, pretty much what was experienced in California. Not yet there, right? But you've already heard from some of the previous speakers that the distributed generation has been growing, and there is also a perception that growth will continue into the future. My previous one of the panelists actually mentioned that this actually poses a problem to the municipalities, given that some of them have got this higher energy charge, which is actually utilized to recover the bulk of their revenue. So with growth, with anticipated growth in distributed generation, this actually leads to revenue losses, right? So when we develop the list cost plan, so we're taking the business as usual tariff with Soni, and then we include the supply side options. And then now on this one here, we test the robustness of the plan, right? We test the robustness of the plan where we basically study what if the tariff composition, the municipal tariff composition, was to be altered, right? Was to be altered in the light of growing penetration of distributed generation as means of mitigating against tariff revenue. All right. So we started the case where the tariff composition is altered over a period of 10 years, where the split is now sitting at 50-50% now. So this actually, we want to know, is this actually signaling the beginning of the new era, where what was previously deemed economically viable under the current tariff composition is now actually brought into questions? Are the diminishing returns that this is going to be pursued by some of the municipalities as long as you remain connected, because increasing your fixed charges significantly from 23% to 50% basically means that irrespective of your energy consumptions, the distributed generation that you're doing is going to obviously, you're going to consume less, but you still have to pay a significantly higher share. Is that still economically viable for you to continue with this? Is there some amount of curtailment? Right. The question we want to know with this analysis is, can the two coexist in an environment where municipalities are revising their tariff composition as means of actually protecting their revenue? Can the distributed generation coexist with in an environment where the tariff is altered like this, right? So this is what we considered in terms of the input assumptions. We considered new PV. We did a solar resource map. We considered new PV as my bad. A brand new wind, second-hand wind, the replacement of the existing PV installation that we got on site. Lithium batteries were part. These are the optimization candidates. Lithium battery, flow batteries, chiller storage capabilities, upgrading existing chillers, LED lightings, diesel engines, biogases with different capacity. It is our expectation that the cost of these options is going to continue to decline. So as part of the assumptions, we use a learning rate from NRO's ATP publication, which basically sees continued declines on PV as well as wind due to declines in the cost of system components, panels, inverters, turbines, racking, etc. Battery modules are likely likewise expected to decline as more and more equipment manufacturers enter the market and compete with each other. So this actually forms part of the input assumptions. Energy efficiency, this is one of the things, like I mentioned, over and above the supply side options that we considered together with the implementation cost. Right, full chronology to cater for spatial as well as the temporal nature of these renewables was considered. So we're no longer using, in fact, we stopped using a low duration case approach when doing capacity expansion studies, because we noticed that renewables have got a specific profile at which they generate energy, and we need to account for that instead of rearranging the generation as well as the demand profile from the highest to the lowest values. So the tool is called Plexus, developed by Energy Exemplar in Australia. It's got full capabilities of doing Monte Carlo simulations. As input, it accepts existing supply options, committed supply options, demand side options, as well as new supply options. And then lastly, we have that luxury of actually stipulating some of the constraints. So the optimization obviously has to meet the resource constraint and that actually forms an input into the study. We can also put in a reserve margins similarly to how the national RP is produced, stipulating the reserve margins or some other constraint. So this actually now leads us to the risk cost plan. So what we're actually seeing when we studied the two cases.
Sorry, just interrupt. 5 minutes if you can trim it there.
Yes, I'm there.
Thanks.
What we're basically seeing, right? So the graph on the left shows the plan under the current tariff, right? And sorry, the graph on the left shows the plan under the current tariff, and the one on the right shows the plan under the new tariff composition. So yes, the answer is distributed generation can still coexist. It's about finding a sweet spot between incentivizing new distributed generation as well as making sure that the municipalities are not bankrupt by this. In terms of the dispatch regime, this is how it actually looks like. You can see that the grid energy share has actually been significantly dropped from 70%, from 90% to 70%. So this is the value of actually having distributed generation on the system. So we can see, right, over and above reducing our CO2 emission footprint. So this actually adds value by minimizing constraint of the grid. Imagine if a lot of the people were doing distributed generation less. So this basically means there's less amount of load shedding that would need to be experienced compared to the case where there wasn't distributed generation. Right? So the research-based plan, we basically adopted the research technology, the battery, the 3 megawatts of battery options, as well as the 200 kilowatts of wind options. And we just basically see to what extent can this actually add value over and above, of course, reducing our CO2 footprint. We can see that the expanded system here shown on the right, called the least cost plus new tariff, significantly reduced the cost, and adding or adopting the research-based technologies on top of the least cost plan had significant values over the period 2020 to 2050. How this is actually dispatched, and you can see that's the profile now as a result of having the battery, a huge amount of battery. This was the business as usual profile. This is the new profile that's lower compared to the business as usual because of the energy efficiency interventions. You can see it doesn't get to 6 here, but by having batteries, you can see the impact of the batteries. The battery is being charged by the grid, as well as the PVs and batteries being dispatched during periods where the tariff is significantly higher, right? So, and of course, the energy share, it's still lower. Right, in terms of grid resilience now, so we basically look at the scenario where we take the least cost plan and we assume that power from Mushwana is not available. So how much of unsafe energy can we meet? How much? So we quantify that, right? So we looked at the representative days and we compare the business as usual, you know, because we expanding our system to have all of these new options, new PVs, efficient lightings, as well as the battery option. So this is how much now, like I mentioned previously, this is the value to the system, reducing the amount of unsafe energy or load shedding, you know, as a result of having distributed or on-site generating. The utilization of diesels are also reduced, though not significantly, and the emissions also not, you know, reduced, but though not significantly. But this is the value now. I just want to emphasize this. This is the value that distributed generation adds to the system, right? It actually means that there's less energy less unsafe energy, and there's less diesel utilization on the national grid, and also means less coal that now needs to be burnt in order to meet demand. So in terms of the summaries, I'll just skip through this. Where we are as CSIR, okay, who gets to benefit from this, right? CSIR has to date added approximately 49 million rands, right? With just having on-site generation. So municipalities can benefit a lot by just incentivizing distributed generations, and also the study offers some insight into how we can restructure the tariff. We're working with a lot of the industry players, the likes of DBSA, as well as Mintech or Sasol. We're doing similar studies for them. The integrated resource plan, and of course we're taking we're considering a lot of scenarios in order to make sure that you cover all angles, you know. So this is, a lot of people can utilize a study like this and find value by pursuing studies like this. I just mentioned a few: commercial, university, schools, residential. Where we're going is CSIR. The next iteration of the integrated resource plan will include a lot of these options here, as well as an outlook on distributed mini grids. Thank you everybody for tuning in. Sorry, my bad. Thank you everybody for tuning in, and yeah, thank you, Chair. Thank you.
Thank you very much, Sipho. I think this is a very good example of perhaps a view which is kind of almost a suburb view, although it does include commercial buildings. It is a view of the optimizations that are possible when one gets really deeply involved. And I thank you as well for reducing the complexity here. There were certainly many portfolios, probably, of scenarios that you had to reduce to produce this presentation. Thank you again so much for that. Okay, I'm going to take your control away and give it to myself. Thanks again. Okay, our next presenter is Crescent Mushwana. Crescent, I think we've spoken to his CV already. Crescent offered to do a follow-on to the CSIR study, and that was specifically around grid impact. So Crescent has a short 10-minute supplementary presentation. And Crescent, if you're available now, I will give control to you. Crescent, your mic is muted at the moment.
Okay, thanks, Marcus. I'm ready.
You're not to be presenter. Okay, control is yours. I will sit back. Thank you.
Okay, thanks, Marcus. This is a very short presentation. It's by no means a detailed grid impact study, but at least a start to complement what we're doing on campus. And there's, of course, a lot of further work that we will be focusing on going forward. So I want to acknowledge my colleagues, Enos and Mpeli, for the analysis that I will be presenting here. Okay, basically this is the overview. Microgrids is basically we see microgrids as a building block of what future power systems will look like. So understanding intricacies around how microgrids are developed, both in terms of energy planning and also grid analysis, we think is critical. And then I'll touch on what we have done on campus currently. And then the grid impact study that was done, basically just looking at voltages and losses as a start and short circuits, and then look at future plans that we have on the campus. So this slide basically just speaks to the thinking that microgrids, we see them as an evolution of the current traditional power system, which we feel will remain with us for many years to come. But microgrids definitely will start to play a much more bigger role, starting even with grids which are currently off-grid, like what Mpeli presented in terms of a microgrid which starts by itself, but further on to be integrated with the entire grid. And linked with this whole microgrid infrastructure, there's a communications and control infrastructure which will become very critical, even at distribution level. At transmission level, we know that most of it is already there. Yeah, basically this is just the outline of our campus currently as we stand. 52 buildings on the CSR campus, and basically that's the consumption that we have on campus. And we're currently, of course, focusing on PV, which we're currently installing in a phased approach. But going into the future, we'll be looking at other technologies, batteries, even including hydrogen, heat storage, as Sipho has presented. Some of the work that is doing is looking into the future in terms of what we can do on campus. So in terms of what we've done on campus, as was presented by Sipho, we currently have close to 2 megawatts peak of installed PV on campus on different buildings. And actually our campus now, I think it has become like a very good platform to already start do some high-level grid impact assessment of installations of PV with the different buildings, basically indicating like standalone systems which are feeding into our 11 kV network. So basically this is what we currently have. And this is the different model that we've developed for our campus, 11 kV grid layout, and with the different PV installations indicated there. And we get our supply from City of Tshwane at 132 kV. We've got 2 15 MVA transformers feeding our campus. And there will be more other technologies which will be implemented on campus as Sipho has presented. But what I'll be presenting now will be like a quick high-level overview of what we have done to assess the impact of the installed PV. It's very important to highlight that all the installed PV was done privately as standalone projects and were installed by consultants. But something which, of course, usually they don't do is to understand what the impact of the installations are on your entire grid, which we had to start looking at internally by ourselves. And there'll be more work that will be done around that. In terms of the first scenario that we looked at, basically just looked at the profiles and short circuit studies. Of course, I wouldn't expect much to change in terms of short circuit studies as we're not changing the grid layout. But on voltage profiles is something that's important to check for each and every building where we've got the PV installation. And at the moment, from what we have checked, there were no violations. And then when we look at the losses, yeah, it was interesting to see the changes in terms of active and reactive power losses as we install more PV on our campus. And as a follow-on to this, of course, there'll be more other work that we'll be doing around power quality and reliability type of studies around the campus. Yeah, so this work basically will speak to that, but it is interesting to see, especially in terms of reactive power, how much drop we have in terms of losses. And at a high level, in terms of losses, of course, it's got financial impacts and all that. And those are the type of things that we'll start to analyze going forward. And then the scenario 2, we looked at minimum loads, and then following the same process in terms of looking at voltage profiles and short circuit, and there were no violations there. And of course, in terms of at the minimum load, both active and reactive power, we saw a slight increase that we observe. And of course, with further analysis and further work that will be done on campus, then we'll be able to see what does it mean in terms of cost and related stuff. So in terms of further work, there's a lot of work that we still need to do on campus. This basically will dovetail on the work that Sipho is currently doing in terms of the energy mix going forward. And one specific one which I want to highlight is the one right at the bottom. We are looking at establishing a real-time digital simulations lab or smart grid lab on campus, where we're going to use our campus as a live platform to test different technologies. And will be technologies which are implemented on campus and technologies which can be tested also in a lab environment before implementation. And we already have started some work in the space with Eskom, who are also looking at establishing a real-time digital simulation laboratory. And work about around the RTDS is very critical for microgrid implementation, to do a whole lot of studies which cannot be done currently using the deterministic approach, where you will need a whole lot of processing power to be able to analyze different scenarios and operating modes, especially of inverter-based generation. Thank you. That's where I'll stop.
Crescent, many thanks. And again, you've reduced a lot of complexity to something quite palatable in a very short time. I appreciate your efforts.
Thank you.
Thank you very much for your presentation.
Sure.
Our next presenter is Aradhna Pandarum, and I'll just get her slide up. There's very little that needs to be said to Aradhna's bio, because she has been introduced before. Aradhna, interestingly enough, was one of my first offers for presentations, because she had done a study on a line and had investigated the implications of voltage impact with the introduction of renewables. So I will, without further ado, I'll give the floor to Aradhna, and we can see what she has for us today. Aradhna, is your audio on?
Hello.
Okay, cool.
That's fine.
Please,
okay.
Please carry on. The floor is yours.
Good. Okay, thank you, Marcus.
Thank you. Cheers.
Good day, everyone. As Marcus has said, I'll be presenting on the impact of renewables, specifically solar PV, on voltage regulation in an MV system. This is based on 2 case studies that were actually done using Dekenah, just to give an idea of the voltage impacts that are experienced with the intermittency from solar PV installations. So the outline of this presentation is as follows. I will take you through some of the challenges faced with installing PV on the network, some of which you have heard previously, some of the guidelines and standards that you need to consider as well, the methodology and scenarios that I used in my case studies for the presentation, and some of the important results from case study 1, which is a constraint network, and then case study 2, which is a non-constraint network. And then I would give you some of the main findings that I've seen and conclusions from the case studies. And lastly, I'll just give you some recommendations to consider when planning for small-scale solar PV on networks. Note that the installations considered in this presentation fall under category A of the grid code, which means that it has a capacity of less than 1 megawatt. So as previously mentioned, there's been an increasing trend in small-scale solar PV in South Africa. This increasing penetration poses risk to the stability of the distribution network. This is due to the fact that power injections from these generators change the magnitude and direction of network power flows, thus causing impact on network operation and planning practices with both technical and economic implications. The stochastic and non-dispatchable nature of the PV output power does not make the situation any better. Some of the technical impacts that can be experienced are the voltage fluctuations, safety and protection issues, frequency-related issues, increased technical losses, and equipment overloading, just to name a few of them. In this presentation, I will take you through 2 case studies that were completed to investigate the impact of increasing penetration of PV on voltage regulation. So voltage management is considered to be an existing problem in the distribution environment. This is due to the aging networks and infrastructure coupled with poor to no maintenance on many of the networks, as well as long spans of poor current carrying conductors. PV has proven to be a technology that is very intermittent in nature, and this means that the output generated can increase and decrease very quickly. This is predominantly due to the fact that the PV production is affected by moving clouds, resulting in uncontrolled variability. This intermittency causes the fluctuations in voltage, and these are not always predictable or are not monitored. And they could occur in timescales which is too fast for our conventional voltage regulation devices to react. So generally, a network is designed for a predetermined voltage regulation limit. This means that a certain voltage drop due to loads as well as a certain voltage rise due to generators are acceptable. These standards have previously been discussed in detail, and I won't actually be taking you through them. But generally, the most important limits to note are the voltage limits for a network to be held plus minus 10%. So it's from 0.95 per unit to about 1.05 per unit. And then the thermal loading of the network and equipment must be less than 85%. The maximum rapid voltage change for generation that is acceptable is 3% for PV generation. The maximum PV penetration that is recommended as per the NRS 107-2-3 for an MV feeder is actually 15% of the peak load of that feeder. This figure is actually based on the maximum change in the LV voltage due to embedded generators of 3%. These limits were considered in the case studies that were completed. So research suggests that the main components to consider when planning for installation of PV on networks are generally the ramping of PV generation due to intermittency caused by fast-moving clouds, the size and the overall penetration limit of the PV systems themselves, and the location of the PV systems. Considering this, the following scenarios were then used in the case studies. So I considered PV penetration level of 15%, 30%, and 50% and 75% of the peak load of the MV feeders. And in each of those penetration cases, I considered the location scenarios of where PV is spread evenly throughout the network, installed only at the beginning of the network, installed only in the middle of the network, and installed only at the end of the network. The PV sizes were calculated as a ratio of the transformer capacity to the overall PV installed capacity. So in terms of the methodology that was used for the case studies, I first analyzed data that was received. So I received data from the Northern Cape Operating Unit from Eskom, and I had to select a non-constrained network and a constrained network. So the criteria for selection of these networks was that the networks had to be in close proximity to IPPs, which had generation data for at least 1 year of the previous year. And I also had to make sure that the demand data was recorded for the same time as the generation data to give you a more realistic result. I then downloaded all the data, including the updated and error-free Dekenah case files for the network. I then defined results for identified buzzbars at the beginning, middle, and end of the network because I was going to be doing temporal studies, so I needed to know to look at the results at these locations as well. I then applied the hourly recorded demand data to the network for the entire year of 2019 and ran simulations to ascertain the base case results for the no PV case. And then the final step was actually to incorporate PV in the represented cases before, as mentioned in the previous slide. And then analysis of all transformer points with the transformer capacities had to also be completed in order to select the points and capacities for the PV installations at the beginning case, middle case, and end PV cases. The PV system in Dekenah was selected and installed on the LV busbar in respective locations. And a power factor of 1 was used because, as I mentioned, this is the category A installations as per the grid code, and that is the requirement. The yearly normalized hourly PV profile for the IPP was then applied as a dynamic characteristic to the active power for the installations with their respective capacities, and this was then depending on the scenarios and the location cases as mentioned. The hourly results for one whole year, which was 2019, for the simulations in each PV case were recorded and analyzed, and then these results were then compared to the no PV case to highlight what findings were actually seen. So this is just the PV model that was used, and as mentioned, I had 8760 generation active power points input into the characteristic, the power factor of 1, and then the constant power factor control mode for the power plants were used. So this is case study 1. The details of the cases will be discussed, but note that the network and the IPP names are confidential and will not be disclosed. So case study 1 was actually a very constrained network, a 22 kV network in the Northern Cape area, with 38 transformers having a total installed capacity of about 2.1 MVA. The backbone length of this network was about 30 kilometers with a total length of about 167 kilometers. Almost half of the network was actually with a single wire earth return conductor installed, and the peak load that was recorded for 2019 was 2.74 MVA. And this was a 0.96 power factor and capacitive load. The end of line voltage was actually less than 0.95 for almost half of the year. And as you can see on the screen, a visual representation of the network is shown, as well as the peak and average hourly demand for the network for the whole year. So obviously, I can't take you through all of the results. There was a lot of data and a lot of results that came out from the study. So I'm just going to highlight the main things that I found. Firstly, I would like to discuss the impact of intermittency generally caused by moving cards on voltage. So the generation data was analyzed with the aim of finding days that had high ramp rates with the generation falling to almost 0. The voltage changes as a result of these ramps were then analyzed, and the results for 5 specific days were selected and tabulated in this table. So the highest ramp rate out of these 5 days was actually almost about 76% of output power that decreased for the plants within 2 hours. This percentage is actually a percentage of installed capacity. It's also interesting to note the effect of the location of the PV plants, and this is quite apparent. So installing at the end of the network results in the highest voltage change in all PV penetration cases when compared to other location scenarios. Furthermore, the penetration of 15% of the peak load actually results in a voltage change in excess of the 3% that's previously mentioned in the end PV cases. This is for all of the days that were selected. The beginning PV location case does not actually result in any case for voltage changes over 3%. And furthermore, the voltage changes do increase with increased PV penetration as expected. It's also important to note that if the temporal resolution of the data is increased, so this was hourly data, if I had minute data or even 15-minute data, I think voltage fluctuations would be more apparent and effectively worsen these results. So this slide shows the impact of the impact to the MV per unit voltage at the beginning, middle, and the end of the line, as well as the overall losses in megawatt for all of the PV location cases, but this was for the 15% PV penetration case. The PV profile gives an indication of the ramps that are experienced that I spoke about earlier, and the resulting voltage changes and losses for each case. The key result here is that the voltage change at the beginning of the network is not so apparent as the end of the line, and I think previous presenters has mentioned this as well. Furthermore, the end PV case or the location scenario makes the most difference as with the previous slide results. The result for this is actually predominantly due to the conductor sizes at the end of the line being very low, thus resulting in overall losses being reduced to a larger extent with PV at the end of the line rather than in other location scenarios. So this graph on the left just gives you an indication of the effect of increasing PV penetration on the voltage for a specific day. The results are actually concurrent to the statement that as PV penetration increases, so will the voltage of the network. The table on the right this shows the number of times the MV voltage actually is in violation of the voltage regulations as given in the standard. Although PV improves the voltage of the network, in this case, the planning limits are actually exceeded in the 15% penetration case. So the MV voltage is over 1.05 in the PV, mid PV, and all PV case for the 15% PV penetration scenario. However, if we want to talk about 95th percentile voltage results, only the 30% and over PV penetration case results in violation. So that is if we're looking at like the quality of supply guidelines in terms of the NRS 048. So this is case study 2. This was not a constrained network. It's also a 22 kV network in the Northern Cape area with 36 transformers that have a total installed capacity of 1.6 MVA. The backbone length for this network was 52 kilometers with a total length of about 114 kilometers. The peak load that was recorded for last year was 1.3 MVA, and this load was 0.9 power factor with a capacitive load. Visual representation of the network and a graphical representation is shown on the slide here. And
Aradhna,
yes.
Apologies for breaking in. 5 minutes, please.
Okay. So this is just the peak and average hourly demand. So here, so just as with the previous case study, I looked at the times that the voltage change is above 3%. And in this case, the 15% PV penetration case does not result in any violations of that sort. Only over the 50% PV penetration case, you tend to see those violations. The slide just gives you a representation of the PV profile and the voltage impacts thereof. The findings is very similar to the previous case, where the NPV case makes the most change and impact to the voltage. This as well, it just shows you that as the PV penetration increases, so does the MV voltage, the per unit voltage increase. And then in terms of the number of times that the voltage is in violation, it is only experienced in the 30% PV penetration case. So the main findings and conclusions from the actual case studies, first I saw that the impact is actually different on a constrained feeder versus a non-constrained feeder. The hosting capacity or the maximum PV penetration may be lower for a constrained feeder, but this also significantly depends on where the PV systems are located. So voltage variation is a main thing to consider when looking at the impact of renewables on a network. It's actually observed that the PV generators can experience high ramp rates due to intermittency and can go as high as 93.4% of installed capacity within 1 hour. And obviously with the high temporal resolution, our South African networks are actually not well equipped to handle. Equipment loading and technical losses is actually improved on a constrained feeder with the addition of PV, but this is to a certain limit. There is a limit or a point at which the losses are actually increased with PV rather than decreased. And as I mentioned, high temporal resolution data will provide more accurate results. So in terms of the recommendations that I would like to make when considering or when planning for PV on a network, data is everything. Also, the PV data and the load data must match temporally. Tools such as SAIEE, PVSYST, SAM, which is a solar advisor model, can be used for radiation data so that you could at least make an estimation of the generation output in a specific area that you want to study. If you have IPP data, this could also be used. Days with large ramps caused by intermittency must be identified, and also remember that the load plays a role as well. In some cases, I've seen that people looking at two extreme cases where maximum generation, minimum load, or minimum generation and maximum load cases. This can be considered, but intermittency must be taken into account. The recommendation of the 15% PV penetration allowed on a network can result in planning violations, especially on constrained network. So I think that I suggest that constrained and non-constrained networks be treated differently. Know your networks and its capabilities. So location of the plant also has impact. So when planning, I think scenarios from my case study couldn't be considered in terms of bulking the beginning, end, or middle, as well as stochastic placement of plants could also be considered. We must be prepared for installations that are not installed to the NRS codes as well. So in terms of inverters and that sort of thing. So that, ladies and gentlemen, brings me to the end of my presentation. Thank you.
Thank you very much, Aradhna. I think the wisdom in your second last sentence there was about know your network. That is certainly the key to many of these things. Many thanks for your presentation and throughout the course of the day, your second presentation. It's much appreciated. Folks, at this stage, we're going to take a 3-minute break. I have 1:30 now on my computer clock. Let us reconvene for the closing thoughts from the keynote speaker and the chairman's 5-minute close off. So 1:33, we'll reconvene now. Thank you.
Right. Good afternoon. Sorry. Good afternoon, colleagues. So the closing remarks or the next presentation now that we are going to enjoy is by Dr. Nhlanhla Mbuli. If you remember earlier, he was our keynote address. So we would like to get some closing remarks from him. Dr. Mbuli, over to you.
Dr. Mbuli, we don't have audio from you. Unmute.
Okay, I'll get this out of my. Okay, thank you, Program Director, for the opportunity for me to give my impressions on how the proceedings have gone today. I wish to comment on two aspects in particular. Firstly, I've observed that today we were greatly blessed to have a diverse mixture of presenters. They came from research environments, consulting background, from Eskom, from municipalities and academia. And I think this has enriched our proceedings today. Secondly, I wish to highlight some of the key observations I made today in terms of the content of presentations without necessarily trying to provide summaries of the individual presentation. Firstly, we had very good information on work done on the resources in South Africa for wind and solar and how the loads will behave when these kind of resources are integrated into the grid. The second highlight I wish to make is on the importance of legislation in ensuring fairness and safety, plus the standards and regulations needed to protect both customers and utilities, and the importance of these in integration of small-scale embedded generation. The third highlight relates to presentations on guidelines, processes, and standards for incorporating renewables, both from the vertically integrated Eskom and also by municipalities, including processes to handle the integration of these renewable energy sources. There was also several studies presented today on potentials for PV uptake, including amounts that can be integrated, solutions for increasing the uptake, factors that influence the uptake, and various statistics on installed rooftop PVs in the country. Another highlight I wish to make is that of work done on microgrids that incorporate various renewable sources, including PV, wind, and batteries, and how to optimize by way of minimizing load shedding in those environments. There was also nice presentations on processes and approach for integrating renewable energy sources in commercial campus, and this presentations highlighted key considerations that need to be made and factors to be considered. I think that's my pick of the highlights. and they were very interesting indeed to hear from the presenters. I think I'm talking on behalf of all attendees when I say the presentations have greatly expanded our understanding and appreciation of this big topic of renewable energy for power integration. And I wish to thank all presenters for putting together such great presentations. Lastly, but certainly not least, I wish again to congratulate the members of the organizing committee for putting together such a great event. With those last words, I wish once more to thank everyone and hand back to you, Program Director. Thank you.
Thank you. Thanks, Dr. Mbuli. Thanks for those words. Let me just get this out of the way. Okay, colleagues, we have come to the end of our session today. And as we started, I think we are just now going full circle. We're going back exactly to where we started, which is I was the first person in the morning, and now I'm going to be the last person as we are closing. So when we opened this morning, I mentioned that we are going to offer you guys, we have the best in the menu, and I really believe that that is what we have delivered. That's what the panelists have delivered to you, these brilliant panelists that spent their time today just imparting knowledge. So I'd like to thank, firstly, again, the organizers, but mainly Marcus Dekenah, who had the responsibility of liaising with the presenters. I know that that was quite a lot of work, and we kept on putting a bit of pressure on you, Marcus. But yeah, good thing that you didn't break under that pressure, and good job. So we'll see what we can get you, maybe a nice glass or a cup. I mean, an award. So I'd also like to pass my thanks to the executives, that is yourself, Lloyd, as well, to the keynote address, Dr. Mbuli. Thanks for spending your time to come and address us. That was a very technical keynote address, and I actually enjoyed it. Sometimes keynote addresses tend to be political, and this one was very technical, and thanks for that. The producer, Minx, thank you for the time that you have spent here. Also, just concentrating on behind the scenes, ensuring that everything runs runs smooth from your side. Thank you for the support. I know that we are also not a very easy bunch to satisfy. We made changes up until the last minute this morning, and you also didn't break under that pressure. Thanks. Please do bear with us even in future. The presenters, I really have no words to thank you. Your contribution was the best this morning. In fact, today, we have seen the different perspectives that you guys came and you shared with the audience, and sometimes one can tell that things are not as easy as they can be when they are seen from far, and you were very, very detailed in your delivery. Thank you so much for that. And mostly the audience, you guys who spent your time, again, more than 230 or so of you that came to listen to us. Thank you so much. And the event is nothing actually without the presenters. I just want to make an announcement that we are going to, or in fact, we are applying for CPD accreditation on this event. and you will be informed how many CPD points are awarded for this event. Just again, your questions and your comments are really motivating, though we are the only ones, the organizers, who can see them, but we really welcome those questions and comments. And as I mentioned in the morning, and we have mentioned throughout the day, those will be they will be forwarded to the presenters, and then they will respond to them, and they will be appended to the material that we are going to publish. Now, just in closing, again, just allow me to share a few or one or two slides, some words of wisdom. A wise man, I hope you can see my screen, a wise man once said that vaping is the renewables of the cigarettes community. And I think he just forgot to mention that the cigar is like that high-end customer, what you call a high LSM customer, who has underfloor heating, etc. All that they want to have is the service. It doesn't matter how much the service costs, as long as they just have the service. Lastly, remember that losses are not good. We always want to minimize losses. We have seen the losses due to the reactive power, etc. So when you do your purchase, go for the supplies that don't have the reactive power components as far as possible. Colleagues, thank you so much. We'll meet again. Please do look out for the published work. I pasted the website for the Load Research Chapter. I pasted it there on the chat box, and I hope that you have seen it. All the presentations will be aired there in due course. Thank you so much. Thanks, everybody. Good afternoon.
Many thanks to you, Mondi. Much appreciated. And thanks to all those that gave us support during the course of this. It is much appreciated from myself, Marcus.
Thanks, Marcus. Cheers, guys.
Thanks, Mora. Thanks, Marcus. Bye-bye.
Cheers then.